Hello everybody, welcome to this review video. Hopefully we'll make it a little bit shorter than last time because I don't want to be here for that long, but we will see how it goes. So there was a doc that was sent out a little while ago from Dr. Watt that just had a list of topics that will be kind of focused on in the final and that you should probably review before you take it. I know it was sent out a little while ago, so I'll be sending out another copy of that same document along with this video when I send it out. As well, I'm just going to be working through topic by topic. That is until we get to the topics that are kind of about like titration and buffer solutions, because we have not yet had the lectures for those topics, and if I explain them in this video, then that would just be the equivalent of doing the lecture, and I don't want to waste anybody's time. So maybe I'll send out like an epilogue to this video, just doing a short little review, going over those subjects once we've had lectures about them. But, okay, let's get into it. So our first topic is density. This is kind of like a measure of how the mass is spread out through a substance. If you remember, it's pretty simple. It's just like density equals mass over volume. This can be in a bunch of different units. Typically you'll see like grams per milliliter is a common one. Then you'll also have like, maybe you see kilograms per centimeter cubed, or any other measure of volume basically. So density is a pretty versatile thing. With it you can do problems like, let's say you have 4 grams of a substance and you have 8 milliliters. Like let's say this is, no, this is just a substance. I don't want to name it. We have 4 grams of a substance and we have 8 milliliters of it. What's the density of this object? And you just do 4 grams divided by 8 milliliters equals one, I guess you could say 0.5 grams per milliliter. If your answer wanted this to be in units of like liters, for example, then you could just use our old conversion factor friends. There's 1,000 milliliters in 1 liter. We put the milliliter on top because we want the milliliter to cancel and be left with liters on the bottom. Then we would just have 500 grams per liter. So we can just easily convert between different units like that. Now we could also have a different problem, like let's say the density of a certain substance is 0.6 grams per milliliter. You have 30 milliliters of something. How many grams of it do you have? Okay, then we could look at this equation that we wrote down earlier, the D equals M over V, and we could just rearrange this so that we can solve for whatever we want. We have volume and we have density. We don't have mass, so if we solve for mass, it's just mass equals density times volume. So then we can just do 0.6 grams per milliliter times 30 milliliters. And then the milliliters cancel out and we're left with grams, which is the unit that we're looking for. And that's going to be, I think 18? I think it's 18 grams. The numbers might be off, I just did that in my head, so hopefully that's right. But that's how you would use this just to solve for a different quantity. You could also imagine that you have D equals mV. Maybe the problem gave you mass and density, but they didn't give you the volume. So then you might just have to switch things around. To solve for V, I would times both sides by V, cancel out on this side, and then I divide both sides by D. On this side it would, on this side it would stay on the bottom, and on this side it would cancel out, and we just get V equals mass divided by density. And then we could just plug in our numbers that way. So that's density. Hopefully that helps. Let's talk about Sig Fig rules. This is a lot of fun. So we should be able to go over this pretty fast for some topics, and we'll also talk about like logarithm significant figures rules, so that that can kind of make a little bit more sense. I know we kind of introduced that sort of recently. But so there are kind of like 3 different categories of Sig Fig rules. We have multiplication / division, Then we have addition / subtraction. And then we have logarithms. Woohoo, we love logarithms, especially in acids and bases. So I'll start with this one, which I think this one is this is the easiest to understand. So essentially, you have like a chain of multiplication and division things. Like I'll write down a bunch of numbers. So let's say we have a number with 2 sig figs. Okay, actually, before I go over the rules, I should go over counting just the number of sig figs in a number. So I'll write down, let's see, I'm going to write down the same number in a few different ways, and then we can compare the number of sig figs in all of them. Okay, so one thing that you should always remember is that leading zeros, which are just any zeros you have up until your first number, they're insignificant. These don't matter like at all. So you pretty much always say that those are insignificant. They can be leading in front of just a number like this. They can be leading when they're after a decimal place. Up until your first number, all 3 of these are insignificant. They don't matter. So that's something that you should remember when we're counting things. Digits like 2 and 3 are significant. So like when you see them like this, then you would say 2 is significant, 3 is significant. Here they're significant, there they're significant, there they're significant. So that's how you'd recognize those ones. And then there are what are called trailing zeros, which are zeros after, say, your last number. Those can either be insignificant or significant depending on the case. Pretty much, if you see a decimal point like this, or right here, then all of the zeros after your last number are significant. So this 0 is after the last number and there's a decimal point. This has 3 sig figs. This one does not have a decimal point, so it's only the number there equals 2 sig figs. This one is like the same number but written in scientific notation. It has a decimal point, 1, 2 zeros. That has 4 sig figs with the 2 numbers there as well. This one has a decimal point, so we have 1, 2, 3, 4, 5 sig figs. All of these leading zeros are insignificant, but trailing zeros can be significant if they have a decimal point. As well, if you have like a number, say 203, any zeros that are between 2 numbers are also significant. So this number has 3 sig figs. So those are the rules for just identifying how many sig figs you have, say, in the description of a problem, they just give you a bunch of numbers. That's how you'd be able to tell how many sig figs those numbers have. So now we can get into these rules for like operations. Let's say here we're doing multiplication and division. Let's say we have this number times that number, let's put a decimal point, divided by this number. The main premise with multiplication and division is that whichever number has the least number of significant figures, that is how many significant figures your answer will have. So I am not really going to do this just off the top of my head, but let's say the answer is like, you plug this into your calculator, it gives you a number that's something wild, a bunch of random numbers, right? So now we're trying to round this to the right number of sig figs. Here we have 2 sig figs. This one has 3 with that decimal point, and this one only has 1. So our answer can only have 1 significant figure. We head to the first number we have here, and because that's only 1, then we round to that place. So 4 is not big enough to round up, so this becomes 500 with only 1 sig fig. Let's say instead that now this number looked like this. This now has 3 sig figs. Now our number with the least number of significant figures here has 2. So now we would go 1 significant figure, 2, and then we'd round there. That rounds to just being 540. That has 2 significant figures. Hopefully that can help you with multiplication and division. I think this is the easiest rule. So now, when we're talking about addition and subtraction, instead of just talking about numbers with the least number of significant figures, now we get worried about decimal places. And there's a couple of reasons why. I'll write down some numbers. So let's say we have a number like this. I'm going to change the number to... We are a Christian university. Okay, so that's our first number. And let's say we're adding the number 0.05. Right? So, if we were looking at this in multiplication and division lenses, then I would say this has 2 sig figs, this only has 1, our answer will only have 1 sig fig, whatever it is. But we're not looking at it quite that way, and I'll tell you a little bit why. So this could be a little bit, imagine you have 2 scales, right? Maybe one scale is really inaccurate, and it's meant for just giving you a ballpark estimate of really high numbers. So maybe you weigh like really heavy things and it would say this is about 430 pounds. But you get really uncertain as soon as you get to the ones place of your weight, or the tenths place or the hundredths place. You don't really know any of that for sure. Then let's say you have a really accurate scale and you add on like this, like 5/100ths of a gram or something, right? Then you might think, well, what will it be if I add it together? Your calculator will tell you the answer is 430.05, but now we need to look at sig figs. What the addition and subtraction rules will tell you is that your like decimal place with like the last significant figure, the highest decimal place with uncertainty, right here, like this is our last sig fig because we don't know this 0. This is insignificant. That's where we round our answer to. Because this one is our last certain digit, we round that digit, and then we just say the rest of it is insignificant, we don't know it. So that would mean our answer rounds to 430. The reason again is this could be 430, this could be 430.1, this could be 432. We just don't know for sure. So because all that uncertainty is there, all of this data right here, we're already uncertain about it. It doesn't really matter. We have to put our, we have to round to this digit, and this one is insignificant. So we can do a few more examples to practice this. Let's say that we have the number 5,403.8, I guess, and we're adding the number 20 to it, or minus. I guess we can do minus. Now we're going to do plus because it's more fun. Your calculator will tell you this is the answer. But now we need to look at the last decimal place of digit of accuracy. This one, 5403.8, this is the last significant digit. But with this 20, we don't have a decimal point, so the last significant digit is right there in the tens place. So we have to round our answer to the tens place. So that means the 5 and the 4 stay the same, 3 doesn't round up 2, so our answer becomes this. Hopefully that is helping. Let's do another one. Let's say we're adding the number 5.3688, and we're adding 0.025. Actually, let's make this 11.025. And we're going to be adding these, but again, all these rules work the same if you're doing subtraction. Then your calculator will tell you have an 8 there. This will be a 13. This will be a 9. This is a 3. There's your 0.6. That is what the answer your calculator will probably tell you. Now we need to look at our significant figures. The last significant figure here is in the 10 hundredths, ten thousandths place. And here it's in the 10 hundredths, thousandths place, the last significant figure, so we need to round to the thousandths place, right there. So then we round our number and we'll get 16.394. Hopefully that helps with addition and subtraction. Let's go on to logarithms. So now, this one is a little bit confusing, I think. We've talked about it kind of recently. Let's say we have a number 3.5 times 10 to the negative 4. Actually, let's do this a little bit more simply. Let's say it's 1.00 times 10 to the negative 4, right? And we take the negative logarithm of this, just because that's what we've been doing a ton with pH recently. Then our answer is going to be something like, your calculator will tell you something like 4.00000, just onwards and onwards, right? Our significant figures is however many significant figures we have in this number here at the beginning, 1.00, so we have 3. That's how many significant figures you will have after the decimal point in your logarithm. So here we have 3 sig figs. This has 3 sig figs, 1, 2, 3. We round to this place. Our number with the correct number of sig figs is this. That may be confusing. You would think it'd be like multiplication or division where we would just have the same number of total significant figures. But now there's this 4 that's showed up, right? Why is it that this 4 does not count as one of the sig figs, right? The thing that's kind of important to remember about the logarithms is in this number up here at the top, we have the number that's actually significant. This is where we measured. This is where any error in our approximation, that's where it is. And then this times 10 to the negative 4, that's just telling us how big our data is. Basically, it's just saying, well, these numbers start at 1, 2, 3, 4, right there. And that's where you start. The 10 to the negative 4 is just telling you how big this is where your uncertainty is. So when you take the negative logarithm of this, essentially what you're doing is you're taking the negative logarithm of the first part, and you're also taking the negative logarithm of the second part, right? And so this is going to tell you exactly how big it is, and it's always going to be some exponent that's before the decimal. So this will give you 4, right? And if this was a 12 or a 13 or whatever, that would give you whatever the number in your answer that will be before the decimal point. And because this is exact, all of these numbers that are before the decimal point are exact too. They're just kind of telling you how big it is. Whereas when you take the negative logarithm of this, you'll get some number. If it's like 3.43, then you won't just get the same number again. But that is where your uncertainty is. Technically, it's, I think, it's 0.000, right? Those digits are where your uncertainty is. And so then when you add these together, you have 4, which is completely accurate. That's confirmed. It's exact. And then you have your measured numbers. That's where your uncertainty is. So let's do some examples super fast. Let's say we took the negative logarithm of this number. I'm going to plug that into my calculator so I can give you actual numbers that you can test with. The negative logarithm of 3.43 times 10 to the negative 3. Your answer that your calculator will tell you is 2.4647006, or I think this is a 5, I rounded it. And then a bunch more digits that we can't really use. So we know that this digit before the logarithm is completely accurate. It sort of comes from this. And then the first, there's 1, 2, 3 digits. So the first 3 digits are significant and we have to round to that. Our answer will be 2.465. And that has the right number of sig figs. Another example, the negative logarithm of say 2 times 10 to the negative 9th. Let's plug that in real quick. That gives you, I think it is 8.6989700004. Now, if we look here, we only have one sig fig. This comes from this exponent is precise. And then we just do one more. That's our last significant figure. Our answer should be 8.7, and just round that. Hopefully that helps with sig figs. Okay, let's move on. We're going to talk about calorimetry. So, we'll talk about two equations that are really important. There's Q equals M times the specific heat times your delta T, your change in temperature. And there's Q equals M times your enthalpy of fusion or your enthalpy of vaporization. And I'll talk about two reasons why we'd use I'll talk about a reason why we'd use this equation and a reason why we'd use this one. So, essentially what this equation is doing is it's helping you to understand that the heat we add or take away from something is related to the mass of the substance, the change in temperature of the substance, and then the specific heat capacity of a substance, which kind of measures the definition of the specific heat of something is it's the amount of heat in joules that it takes to raise 1 gram of a substance 1 degree Celsius. So say I like to use the example of water and your seatbelt in a car. If you leave like a cup of water in your car during like a hot summer day, then it's going to get warm, right? But it won't be scalding you. It rose in temperature like some. However, if you compare that to like your seatbelt that got left in the same car during the summer day, you come in and you touch that and it like stings. It hurts so much. That's because the metal of the seatbelt, it doesn't take a lot of heat to change its temperature very much, which means it has a low specific heat capacity, right? The amount of joules it takes to raise 1 gram of 1 degree Celsius, it doesn't take very many joules to raise it, so it's a small heat capacity. But water, it takes a lot of heat in order to raise 1 gram of water 1 degree Celsius, so it has a much higher heat capacity, specific heat capacity, and that's what SH means. So, if you say wanted to find the amount of heat it takes to raise 54 grams of water 15 degrees Celsius, or let's say you wanted to warm water from 45 degrees Celsius to 60 degrees Celsius. I'll say this is T final and this is T initial. And then we also just know that the specific heat of water is, you could say it's either 4.184 joules per gram degree Celsius, or it's 1 calorie per gram degrees Celsius. Just make sure you use the right specific heat value depending on what units they want in your answer. I'm just going to use this joule. I'm going to use the calories one because it's really nice. But if I wanted to find Q, I just plug this in. This is M. Our change in temperature is our final temperature minus our initial temperature. So like T final minus T initial. 60 minus 45 is 15, right? And then this is our specific heat. So I plug in 54 times 1 calorie per gram degrees Celsius. This is in grams. Times 15 degrees Celsius. You'll notice that the grams cancel out and the degrees Celsius cancel out as well, and we're left with just a unit of calories. If you multiply those numbers, that's our Q. Now if you wanted to, of course, because this is chemistry, they might give you the amount of heat it took to raise something, and then they might give you 2 of these other variables. Maybe they give you mass and the change in temperature. You just have to use algebra to solve for specific heat. So let's say they asked you what your specific heat was and they gave you the other 2. To solve for that, divide both sides by M. those cancel. Divide both sides by delta T. Those cancel. Now we have specific heat equals the amount of heat it took divided by how much of the substance you had in grams and divided by how much it went up in temperature. And then boom. So that's how you do that algebraically. So I talked a lot about that equation, this one right here, and I'll talk about an exception. And here I just wrote them in different order to this equation. So let's talk about, like, say you have a glass, or maybe you have a water bottle that you froze in your freezer for some reason. Now, if it's just gotten to the melting point of water, so let's say this is it at the beginning, all of it has just barely gotten to 0 degrees Celsius. So that means it's going to start to melt, right? So if we did the temperature of this right there, it'd be 0 degrees Celsius. Now, if we melted some of it, so now we have just like big chunks of ice floating in it. If we measured the temperature of this part, or anywhere in the substance really, it would all still be 0 degrees Celsius. Now, if we measure it up until the point where there's just a little bit of ice in it, and the rest of it is water, all of it is still 0 degrees Celsius. The material will stay at the melting point or the boiling point until all of it has changed phases. And then it can start to raise the temperature again. Now, if we use this equation, this would kind of not work, right? Like, let's say I was trying to figure out the amount of heat it took to melt this glass of ice to be completely water. Then I'd say, well, our heat is equal to our mass, and then is equal to our change in temperature. But hang on, there's no change in temperature for this whole phase change. It's 0 degrees the whole time. So then that would tell us Q equals 0. And we know that we're adding heat to it, right? Like, that doesn't make sense. So that's why we have a different equation, this guy over here. Basically, chemists were like, how about we just measure the amount of heat it takes to change 1 gram of a substance from ice to water, or from water to steam, right? That is what your delta H is. It's your change in enthalpy. And so this can either be about, like, the melting point, so say you're melting ice or melting a solid of anything, or you're freezing it, then you're concerned with this one. It's the delta H of fusion. Now let's say you're boiling something, or maybe you're condensing it, bringing it from a gas to a liquid, then you're concerned with the delta H of vaporization. And then all you have to do is, this is in units of joules per gram or calories per gram. Same with this one. Just times this amount by whatever the mass of your substance is, and you found out how much heat it took to melt all of it, or to freeze all of it, or to boil all of it, or to condense all of it. So, yes, you may have seen this graph before, and I'll talk about what's going on here. We have heat right here, heat added. So it's saying, like, as I move this way, I just keep adding heat into it. Maybe I'm microwaving it the whole time, I don't know. And here we have temperature, right? As you go up this way, your temperature is increasing. So, like, here might be 0 degrees. Here might be 100 degrees. Now you'll notice that there are 2 points. I drew it kind of lazily, so they're not perfect, but they should be flat, right? Where the temperature isn't going up, even though we're still adding heat. These are phase changes. So this one is likely you're melting the substance, and here you're boiling it, right? Here we need to use this equation. Q equals M delta H, and this one is a fusion. In this place we need to use Q equals M delta H of vaporization. And then everywhere else, we're just increasing in temperature. We can use this equation again, like normally. So Q equals MSH delta T. And same here. And so those are the periods when you're using those equations. Let's say you have a problem that told you you have a certain mass of a substance and it starts at this temperature and you want to heat it to this temperature. Then you have to be careful to use your equations for each interval that you move across. So let's say we have to have Q equals M times specific heat times delta T for this little part right here, where it goes up to 0. Then we have to use this equation for this part where it's changing phase. Then we have to use this equation for this part where you're going up from 0 degrees to 100 degrees. Then you have to use this equation for this period when you're boiling. And then you use this equation finally for this little part between 100 degrees and your final temperature. Hopefully that should help you know when to use and apply these. Yeah, so I think we can move on now. We're going to talk a little bit about bomb calorimetry, which is really related to these concepts that we just talked about. Essentially, chemists were like, how can I measure how much energy something has in it? And they're like, well, if you take a certain amount of it and you put it in a little box right in here, let's say it's a cookie or something, we burn it in there, that cookie will release a certain amount of heat, just depending on how much energy it has stored into it. If that box lets all of the heat to go into a tank of water around it, right? Well, we can measure how much the temperature in that water goes up. And if we know the mass of the water in there, and we do know the specific heat of the water, then we can know how much heat the cookie let out. And then we can say, well, that cookie had about this many calories in it. That's how all of the food in like grocery stores measures how much calories something has. Or maybe they'll just burn like ingredients in a calorimeter like this, and then they'll add up totals. So that's kind of how a calorimeter works. You need water, you need a temperature gauge in there, you need a box to burn your thing in, you need some way to light it. That's how it works. So I think we're okay to move on. So there are a few different types of energy. There are two like really important ones. There's positional, there's potential energy. And then there's kinetic energy. The most important thing to remember between the two of these is that kinetic energy is motion. So not only does that mean like when I'm running around, like, whoo, I got a lot of kinetic energy like that right there. Not only is it when you're moving, right? It's also when like molecules and atoms are moving. So something like temperature is actually a measure of the kinetic energy of particles. It's measuring how fast they're moving, right? So that's what kinetic energy is. It's just motion. Something is moving and that gives it kinetic energy. Potential energy, at least for the uses of this class, is pretty much just energy based on like position. So it might be something like you're standing at the top of a cliff, you have a lot of gravitational potential energy. You could emit a lot of energy depending on what you decide to do. So those are kind of the most important concepts for this sort of thing. I would definitely just be aware of kinetic energy, most importantly. So yeah, okay, I think we're good there. Let's move on. So we're going to talk about electron configurations again. I know it's been a little while since we talked about this. So it may be more useful to talk about, say, orbitals and like the Hund's rule and Aufbau principles before we talk about electron configurations. So just remember, there are really just kind of like three different categories of orbitals that we really talked a lot about in this class. We have kind of the most basic kind of orbital, It's just shaped like a sphere, right? Like imagine it's a sphere and not just a circle. So this is an s orbital. That's what it looks like. It's kind of the first type of orbital you'll see. There's a block of the periodic table. Maybe I'll try and just freehand a periodic table down here. Okay, so the periodic table kind of looks something like this. Sorry, I know it's not perfect. But the s orbital is kind of the first orbital that you have, and it's typically shown in this block. In this whole block, the s orbital is the outermost orbital. This one fills up first. It's kind of like you start here, and then you move this way, and then you move to the next row, and then you keep filling up like this. So our next type of orbital is what's called a p orbital. There are some different shapes now. A p orbital looks more like a dumbbell, like this, where it's really thin here at the middle by the nucleus, and then it's wider out here. And it can either look like it's vertical, or it can look like it's coming forward in the x direction, or it can look like it's coming in the z direction. So there are three different orientations of the p orbital. In a sense, there's only one kind of s orbital. It's only got one orientation. But with p, you have three different orientations, right? So this means technically you have three separate p orbitals. And there's only one s orbital. Now we'll come on and we'll talk a little bit more about a d orbital. There are 5 of them. They kind of are in this block right here, the transition metals. This block is mostly p blocks. So here we have stuff that looks like we have 2 dumbbells, most often. I won't draw all of the shapes, but most of them look like this. And you'll have like a clover like this, you'll rearrange it this way, you'll have one flat, you'll rearrange it this way. And then there's one more which looks like a dumbbell with like a donut around it. No, it's not perfectly drawn, but that's kind of the cooler looking one, I think. And there are 5 different orientations of d orbitals. And so we have 1 s orbital, 3 p orbitals, and 5 d orbitals. And really after that we have f orbitals. There are 7 of them, and we don't really worry about them in this class. Now, in each orbital, you can hold 2 electrons. You can kind of think of it as there's only space in there for 2 of them, and they have to be moving opposite to each other. They don't like being close to each other. So here we might have 1 electron kind of doing a spin up, is what we call it, and then another electron doing a spin down. And then in p, we would also have electrons, 2 in each orbital. That's like the maximum that they can hold. They don't have to be filled, but in theory that's what would happen. They would all have a spin up, and then they would have a spin down, and then same with these ones. So you can think there are maximum 2 electrons in my s orbital, there are maximum 6 electrons in my p orbitals, and there are maximum 10 electrons in my d orbitals, because there's 5 orbitals, 2 electrons in each of them. And that's, in theory, how many electrons those could hold. So now, when we're moving along the periodic table, we just kind of think about, as our atomic number increases, the number of electrons increases as well. So here, this is hydrogen, has only 1 electron. It fills up the s orbital first. So then, it's just got an s, and it's just got 1 electron in it. Now if we were to come to helium, it has 1 more electron than hydrogen. It fills up the s orbital, and then boom, that's the energy level done. So now that we've talked about all these different types of orbitals, the important thing is, as you go up in energy levels, which is kind of like you're adding, like let's say here's your nucleus right there, and an energy level is like a ring of orbitals around it. It's kind of like how far from the center you're going. So let's say it's kind of like Bohr's model, if you remember that, or like a jawbreaker, if you've like licked half of it away and you can just see all the rings on the inside. So here's like the first energy level. This is 1. and then here's the second energy level. This is 2. It's like you've added so many electrons on this first energy level that now any more you add have to be pushed out to this second energy level, if that kind of makes sense. Because electrons don't want to be close by each other. So as you go out in energy levels, it's like you have a new larger type of each orbital. And you begin to add on more types of orbitals the farther you go out. So I'm going to erase these drawings. On your first energy level, you have only one type of orbital. You have s orbitals, the sphere, right? Now, we've finished our first energy level here. Now let's imagine we're coming down to the next row of the periodic table. The second energy level, we have an s orbital, but now we've finally started our first row that includes p orbitals. So now we have one s orbital, and then this is a 2, just meaning it's on the second energy level. We have a 2p, and then we have 2 other kinds, right? So we have 2p and another 2p. They're kind of 3 orbitals. So, like there's 2 elements here. I think this is lithium and beryllium. In theory, let's this work forwards as if we were filling orbitals. We do 1, 2 in the s's. So boom, boom, and then the 2s, there's 1 there. The beryllium has 1 more. And now we can start filling our p orbitals. There's 6 total elements here. Now let's imagine we have, I think it's boron next, and then carbon adds another one, and then nitrogen adds another one, then oxygen adds 1 more, then fluorine 1 more, and then neon adds the last one. And now we filled the entire second energy level. We're right here. You can look at this whole row here, the noble gases, as being the last row. We filled our whole energy level. So, in doing that, I kind of did a few principles that will help you when you're just trying to fill up orbitals and understand configurations like this. What I did is I started at the lowest energy level, 1. I filled it up completely with however many electrons I could, and then I moved to the next highest energy orbital. So I moved from 1s, and then I went to 2s, and then I went to 2p. If I had more electrons, I would go to 3s, and then to 3p, and then to 4s, and then to 3d, and then to 4p, and so on. You fill from the bottom up. It's kind of like if you were filling a glass of water, right? Would you expect that you got like a thin layer of water here at the top, and then it would progressively fill downwards like that? No, water would fill from the bottom. You'd start here, and then it would slowly trickle up, right? That's exactly what we're doing with these orbitals. This is like the lowest energy. It moves up in energy the farther you go, moving like this. Another thing that I did, you may have noticed, is that when I added electrons to these 2p orbitals, they're at like the same energy level, right? So they're kind of equivalent to each other. I would add an electron to one of them, and then I would move to the next one and add an electron before I added a second electron to the first one. That's important. A good analogy for this, I think this is called Hund's rule, is based on like library tables. Let's say 2 people can sit at each library table, and none of you know each other, so you don't really want to be really that close to each other, right? So I would come in and I would sit right here, right? Now let's say another person was coming in to find another seat, or I don't know why I drew them that way, but do you think a person who doesn't want to sit by somebody else, and they have 2 empty library tables, and there's one person sitting at this one, they're not going to come sit right here, right? That would be kind of awkward and uncomfortable. They're going to go to these ones first. So a person will come and sit at this one. And then a person will come and sit at this one. And then, once a 4th person has entered and everybody has 1, then finally somebody will sit here. And then somebody will sit here. And then somebody will sit here. That's Hund's rule. Is that you'll put 1 electron in each orbital before double filling another one, like this. So, now that we've finally established that, then we can finally go on and do a little bit about electron configurations. Electron configurations is where you just represent an element by by showing those orbitals and showing how many of them are filled and so on. So again, if I was to represent hydrogen, then I just think, okay, we start at the 1s orbital, and we only have one electron, so that's 1s, and then I'd put a 1 here to show we have one electron in it. If I was representing helium, I would say helium equals, we start at the 1s energy level, we have 1, 2, and then we're done, we're out of electrons, we stop there. Then I could think about lithium. Let's just write lithium here. We start at the 1s energy level, we have 2 electrons, we fill that one, we finish the energy level, we move to the next highest orbital, that's 2s. So then I think 2s here, and we have only one more electron. That's it, we're done. Now if I think about, say, let's do oxygen here. Now I start at my basic ones, 1, 2, we fill up the 1s energy level, we have 2 electrons in there. Then we do 2s right here, 2s, 2, we fill that up, we still have 4 more electrons. Our next highest type of orbital is 2p, and we do, it's like I'm just going to draw it over here. We put 1 here, and then 1 there, and then 1 there. And now we have 1 in each, so then I move there, and now we're done. We're completely filled. So there's 4 electrons in there, 2p, 4. That's our electron configuration for oxygen. Now what scientists figured out, and because we as humans kind of tend to notice this, is when you're writing electron configurations for elements down here, you start to get a lot of orbitals written, and it gets kind of annoying to write so much stuff. So what they tend to like to do is they like to do shortcuts where they'll just write the name of the most recent noble gas or anything in this last row, and then they'll do the electron configuration from there. So if I was going to do the electron configuration of oxygen, but in this abbreviated way, then I would write oxygen equals helium, and then move on from helium's configuration, which is 1s2, and then I'd say the next one is 2s2, and then 2p4. So if we wanted to do another example of this, let me look at my periodic table here. Let's say we wanted to do sodium, which is right here. It's on this 3rd row. Then the last noble gas before that is neon, right there. And then I would write Na equals neon. And then just the next one, the next highest energy level is 3s. And we only have 1 left, so we put 3s1, and then we're done. It's much shorter than having to write all of this out before 3s1, all right? So now we'll talk just a little bit about like d orbitals. If I was going to draw like a diagram of like how high of energy different types of orbitals are, we have 1s, it's here at the bottom, it's the lowest energy. Then we move up to the next one, 2s. And then as we're on the 2nd energy level, we now have a type of orbital called a p orbital, 2p. It's higher in energy than 2s is, but not by a ton. You'll see it's a little bit less than this difference. Then we'll move up and we'll have 3s, and then we'll have 3p. And now, on the 3rd energy level, we'll introduce a new type of orbital called a d orbital. Now the thing about the d orbital is it's a little bit higher in energy than a 3p orbital. However, if we go to the next highest s orbital, it's actually like just a little bit lower than the 3d one is. So if I was to draw these in terms of height, this would be, we'd go to this one, then to this one, then to this one, then to this one, and you might think we go to the d orbital next, but in reality we go to the 4s because it's just a little bit lower energy than 3d. So it's kind of like we shoot over to 4s and then to 3d, and then we would go to like 4p. So in electron configurations of like say a transition metal, it might be useful to pull up a periodic table to look and compare this against. Let's say I was doing the electron configuration of scandium, Sc. basically I would do the last noble gas, so say argon, brackets, and then I would go to the next energy level. We just finished 3p. Then the next one is 4s with potassium, right? So we fill up 4s, and then we have two electrons there. And now we can go to 3d, and we only have one electron left, so it's 4s2, 3d1. That's why Ds work kind of strangely like that. As well, in the d orbitals, there's a few little small exceptions. The 4s energy level and the 3d are really close. And another thing about orbitals is they really like being stable. So like a lot of elements will try and get to a full octet, like they'll try and fill their orbitals completely. When an entire set of orbitals is filled completely like this, that feels really stable. And sometimes elements will take electrons from other orbitals in order to make that happen, especially because 4s and 3d are so close. So let's say these are our 3d orbitals, and this is our 4s. Now let's say this happens specifically with copper, Cu. It will have 2 in the 4s, and then we'll have 9 in the 3d orbital. And if it just had one more electron here, this would be super stable, and it would feel great. So what copper tends to do is, because these are so close, this stability would be so nice that it steals an electron from 4s to do it, right? So if we wrote copper, the electron configuration would be argon, and then it would be 4s1, because it's stolen an electron from here, and then we would write 3d10. And then once you got to zinc just solves this problem, says, okay, we add one more electron, it goes right there. Now we're chill, back to normal. So copper and the other elements that are in the same group, above it and below it, let's like say silver, might do something like this with the energy levels. There's also one more that does this. It's chromium, which is, I think, Cr. Chromium doesn't have it completely filled. Instead, it has 4 in each, right? So it has 1 here, 1 here, 1 here, 1 there. And it says, if I had just one more electron in here, that would give me a pretty good sense of stability. So I'm going to steal one from 4s to do it, like this. And so then, if we were to write the electron configuration of that, it would be argon, because that's the last noble gas, then 4s1, and then 3d5. And now we've done it. And so the other ones in the same group as chromium will often do this too, like molybdenum will do this. So those are just a few of the only exceptions to the normal pattern of just filling normally. If you want to know a neat little way to remember the order that you should fill orbitals, there's a really nice thing you can do where you kind of write this sequential stair going like this. So we'll have 1 here, 2, 3, 4, 5, 6, 7. These are just energy levels going downwards. And then let's say we have our types of orbitals over here. So we have S and P and D and F and yada, yada, yada. We don't care about that. So on our first energy level, we have 1s, and that's it. Our second energy level, we have 2s and 2p, and that's it. On our next energy level, we have 3s and 3p, and then 3d, and that's it. On 4, we have 4s, 4p, 4d, 4f, and yada, yada, yada. There's no more, actually, on 4. And then 5, you have 5s, 5p, 5d, 5f. We don't care about this. And then we can just continue filling out to these lower energy levels. Don't need a dot there. This is 7s, 7p, 7d, and 7f. And essentially what we would do is we draw diagonal arrows going down like this. And we fill orbitals in the direction of these arrows. So it's like I start at this very beginning arrow and I follow it down this way. So I fill in 1s and we finish the arrow. So we move to the next one. And then I fill the 2s, finish the arrow, move to the next one. Then I fill the 2p and the 3s. Okay, we're good. Then I fill the 3p and the 4s. And then I fill the 3d and then the 4p and then the 5s. And then I fill the 4d and then the 5p and then the 6s. And now I fill the 4f and then the 5d and then the 6p and then the 7s and so on. That can help you if you're trying to remember the order that you're filling them in, especially for these larger ones. I don't expect that you'll need to do that really heavily for the final though. Okay, so I think that is pretty good cover of orbitals and say like abbreviated electron configurations. The Aufbau principle again is that you fill from the bottom up. You fill from the lowest energy level to the higher energy levels. And then the Hund's rule is just that you would fill each type of orbital with 1 electron before you put 2 of them in. So, okay, we're going to move on. And I'm actually going to pause the video for a little bit because I have not drinking some water and I would like to do so. So, see you soon. All right, so moving on now. We're going to talk about trends on the periodic table. I'll draw it again. It's a great periodic table, very lumpy. But let's talk about some things, especially atomic size. So there are a few factors that affect atomic size. You could think one of them is your energy level, right? We talked that your lower energy levels are closer to the nucleus. If you have larger energy levels, so like say 2 or 3 or 4 or 5, those are going to be farther away from the nucleus. That's going to make your atom larger, which means as you go down the periodic table this way, your size will get bigger. So I'll put size here to mean maximum size. Now if we think left to right, we need to think about like the charge of the nucleus compared to the charge of electrons. So let's say over here we have like, there's only 1 electron in its outer ring and there's a nucleus over here. There's a bunch of rings inside this, it may be, but we're just thinking about the outermost ring because that's where the size of the atom is going to change. So you could think there's only 1 little bit of charge over here compared to the same amount of charge in the nucleus. That's not going to attract it very strongly. But as we move this way, then we get more electrons in that outer ring. They don't get any farther away from the nucleus, but the nucleus has a greater charge that's better able to pull them in. They refer to it as an increasing effective charge. That means as you go this way on the table, your atom size will shrink. So essentially, let me erase this a little bit. Your atomic size will be greatest over here, least over here, and your size will be greatest towards the bottom of the table and least towards the top. So in theory, your largest atom will be right here, and your smallest atom will be over here. Those are the trends with atomic size. Now, we'll talk about 2 more. There's ionization energy. And there's electronegativity. So these 2 may seem really similar, and they're related, but they kind of mean different things. So electronegativity is kind of how badly does this atom want to acquire electrons, right? So you could say fluorine, for example, has 7 electrons in its valence shell, which valence just means the outermost energy shell, and that's just going to be an s orbital and a p orbital. If it has 7 and it gets 1 more, 8 electrons in that shell, it will be really stable. It'll be really stable, and essentially atoms want to get to that state where they have 8 electrons in their valence shell. So fluorine, which is like right here, if it gets 1 more electron, it will be like it has the same amount of electrons in its outer shell as neon, which is just chilling, it's happy. So fluorine desperately wants 1 more electron. it has a really high electronegativity. That's kind of what that means. Now oxygen, which is right next to it, you know, it wants electrons like fluorine does, but the problem is oxygen has 6 valence electrons. It would need to get 2 in order to get there. So because it's almost like a little bit less realistic for oxygen to be able to get there easily, it has a slightly lower electronegativity. And then you could even think nitrogen, which is 3 electrons away from a full valence shell, is just like, it'll take a little bit. It's pretty hard for me to achieve that. It has a lower electronegativity than fluorine and oxygen. Then we could just jump all the way over here to, like, say, lithium. Lithium doesn't even really want, in no way is it going to be able to get 7 more electrons to fill the shell. Lithium has a smarter game plan. He says, if I just lose an electron, then I'll get to a full valence shell that's just underneath it. It's like, I could just lose one, and then I go backwards, and then I get to that full valence configuration anyway. So in a sense, lithium has a really low electronegativity because it doesn't want to acquire a ton of electrons. So you can say your electronegativity increases this way, right? Now again, as we move up and down in energy levels, that's like the farther away we get from the nucleus, right? Now, the nucleus is the positive charge that kind of attracts an electron. If we're farther away from that positive charge, we'll be less able to pick up an electron, which means as we go down the periodic table, we get less electronegative, which means the most electronegative elements will be at the top. So if we write our trends, they're just going the opposite direction that our size trends are. So size will be biggest down here, electronegativity will be biggest over here. Okay, so now let's talk about ionization energy. Whereas electronegativity is a measure of how badly an element wants an electron, ionization energy is a measure of how much energy does it take to rip off an electron from that element. Like, how hard is it to pull an electron away from it? We can actually think that because fluorine really, really wants electrons, you can stand to think that, man, it's going to be hard to steal an electron from it, right? That's going to take a ton of energy. It's going to have a high ionization energy. Because oxygen's electronegativity is a little lower, it wants electrons a little bit less desperately, it's going to take a little bit less ionization energy to pull an electron off of it, and so on and so forth. To lithium, you know, lithium almost wants to lose an electron. It would be convenient for lithium to go to this place, so it has a really low, it doesn't take very much effort to rip off an electron. Ionization energy will be bigger over here. And now the same, because the charge is in the middle and the farther away you get from the nucleus, an electron out here will not be as close to the charge as an electron right here. So the farther you are away from it, the bigger your energy level is, the easier it is to rip off an electron on the outermost ring, which means your ionization energy will not be very big here. It won't take a lot of effort to rip that off. Versus here, you're close to the nucleus, it takes a lot of energy to steal it. So your ionization energy is also opposite to your size trends. It will be really small in this corner, bigger this way, and bigger this way, and it will be highest over here. Okay, those are your periodic trends. Let's move on. So now we're going to talk a little bit about radioactivity. Sorry, my throat is getting dry. Radioactivity kind of involves when an atom or a nucleus is kind of unstable. So we will try and like a nucleus is just like a bunch of different particles, right? There's lots of neutrons and protons, and they're just kind of all sitting together in this clump, like this. And it's saying, you know, this is really unstable, it's shifting a lot. Maybe I could make things a little bit better if I shot something out. So there are a few different types of radioactivity, but this document only talks about really one that we need to go over, and you feel free to go over the other ones. Like there's beta decay, gamma decay, all those other ones. But this one mentions alpha decay, which is where you spit out an alpha particle. The symbol kind of looks like this. That's the Greek letter alpha. And an alpha particle is really just a helium atom, which has 2 protons and 4 total mass number, which means it has 2 protons and 2 neutrons. Now, it also is missing 2 electrons, so it has a positive charge on it, like this. Essentially, because you know that mass is conserved here, right? We can think of whatever we started with, like let's say it was carbon 14. So I believe carbon has 6 protons, and it has 14 total for its mass number. Let's say this undergoes alpha decay. That means you're going to spit out a helium atom like this, He2+. And then you're just thinking, okay, well, I got rid of 2 of my protons. I must have something with 4 protons. And I got rid of 4 of my mass number. I must have 10 for my mass number. And then this is going to be a different element, right? Because we lost protons. I'm going to say this is 4. That's going to be hydrogen, helium, lithium, beryllium. This is beryllium. And there you go. That's kind of what undergoing alpha decay is. You just make sure that the numbers for your atomic number, which is like your number of protons, add up on both sides, and then your mass number will add up on both sides. So really that's all there is to it. That's alpha decay. That's what it looks like. That's what an equation looks like. They might tell you that this undergoes alpha decay. What's the other particle? We figured out what it was. It was beryllium. Well, they might say something underwent alpha decay and produced this. What was the original thing? Then you might say, okay, well, if we just add up these protons, it will have 6 protons. Then we'll have 14 for the mass number. What element has 6 protons? There's beryllium is the 4th, then there's boron, and then there's carbon. There it is, carbon 14. Those are some pretty good examples of alpha decay problems. Okay, we can move on. Now let's talk about molecular shape. I think that this one can be pretty confusing. It really helps to try and think about it in like a 3D kind of way. So I'm going to write down a bunch of different examples of molecules, and then we're going to draw the shapes and try and understand what they look like. So then we'll draw this one, then okay, so this is going to be our 5 shapes, right? Yeah, apparently these are too high, I've been informed, unfortunately. Sorry for our technical difficulties. I'll draw the Lewis dot structures of each of these shapes so we can understand exactly what's going on. This one we have carbon in the middle. It's double bonded to oxygens on both sides. This is completely balanced on both sides, right? There's electronegativity over there that's the same as this one, double bonded both ways. This is balanced and it's straight. The shape of this is linear. Now, you have to be sure that it's completely balanced on both sides. So let's say that instead of oxygens on one of these, we had, say, sulfur. Now, sulfur has a smaller electronegativity than oxygen. That means the electrons in these bonds, they'll be drawn more closely to oxygen, which means there's a more positive charge on this end, which is going to, it won't affect the shape, but it will make this molecule polar. Polar just means that it has a slight imbalance of charge somewhere on the molecule. This can happen if the shape is linear, like I just showed you, or it can happen if, say, this central atom is maybe, it has lone pairs on it. So if we had nitrogen here, and it was bonded to, say, a fluorine and then an oxygen over here, if we were to balance everything, this has 3 lone pairs, this would have 1 lone pair as well. You might think this is going to be linear like carbon, right? but this lone pair on the nitrogen has a pretty dense negative charge. It pushes those bonds slightly away from it. So really what it looks like is this. This is a bent shape. This is bent. You can know because it has two bonds and there are lone pairs on the central one that's making it bend like that. So now let's come over to this kind of tetrahedral, this kind of geometry. We'll have boron in the middle, and then it will be bonded to a fluorine. It has three fluorines that it's bonded to. And I'll just leave out the lone pairs on the fluorines, but there's no lone pairs on the boron. This is a shape that kind of looks like you took a circle and you split it into thirds, or it might look like a fidget spinner. I think that's kind of a related shape. This is trigonal planar. Essentially, you can kind of think triangle, and then planar just means it's flat. It's on a thin plane. You think if I could hit all of these with one sheet of paper, just going like this, then it's on a plane. This is triangle planar, or trigonal, you'll see. Trigonal planar. And that's what this shape is. You can think it's a flat triangle, that's what it will be. Now if we removed one of these fluorines and say this was a lone pair now, then we have the bent shape that we talked about a little bit ago. So now we can move on to the next shape. We have our C in the middle, and then we have an H over here, and then we have an H right there, and then we have an H right here. So if you're looking at this, you might think this is a flat square, but the important thing is to remember that this is 3D, right? And because they want to get as far away from each other as possible, electrons are figuring, like, we could just be a square, like if we imagine all my arms and legs are bonds. I don't even know if you can see my legs in the video. Probably not. But like, imagine my legs are just going flat this way. They're thinking, man, we could get a little bit farther away from each other if we rotated. So they kind of form like a tetrahedron shape. So like if the C is in the middle here, we have an H coming up, and we have an H going to this corner. We have an H almost coming forward out of the whiteboard, and then an H going backwards back here. They call it a tetrahedral shape because if you imagine like a dotted line between each of these, then we have four sides to the shape, and it's like a triangle pyramid where there's a triangle base here, and then there's a top, and all three corners go to it. So that's why it's called tetrahedral. Now, if you can kind of imagine this shape where you have a C there and an H here, and an H there and an H back there. Let's say instead of this top H being a bond to a molecule, let's say it became a lone pair. Then that lone pair would push those other H's downwards, and you would kind of have almost like a triangle shape like this, right? However, instead of being flat like this, we have like the carbon on top. So it's like we have kind of like a shallow pyramid. If you draw dotted lines between all of these molecules, it's like we have a shallow pyramid. So this is called like trigonal, meaning triangle, it's still a triangle. Trigonal pyramidal. This will be polar because there's a dense negative charge by the carbon that pushes those ones away. So that's what trigonal pyramidal means, is when you have a lone pair like that pushing three other ones down. Now, if you replace another one of these with another lone pair, so something like looks like that, then in a sense we've just found another way to draw a bent molecule, right? Because it's just C, and then there's an H, and there's another H, and it's just bent like that. So, yes. Now we'll move on to this next one. This one's a little tricky to understand, so I'll try and draw it well. It's like we have a phosphorus here, and then we have 5 fluorines. So there's one that comes directly up and one that comes directly down. These are like polar. They're because it's like the North Pole up here and the South Pole here, if you can kind of visualize that. And then we'll have 3 more fluorines. So one that comes out this way, one that goes backwards into the page, and then one that like comes forward out of the page here. So it's like we have one above, one down here, and then we have 1, 2, 3, all in this same axis. So it's almost like we have a trigonal pyramidal shape where these are just forming a flat triangle, and then we have a fluorine above and a fluorine below us. Now, if you want, you could imagine lines between these. It's kind of like we have a trigonal, a triangular pyramid on top, right? Because there's a triangle base and then there's a top pyramid. And then there's like another one down here that we form with this bottom fluorine. So what they call this shape is trigonal bipyramidal. Or triangle two pyramids, right? That's why that shape is called that. We could go into more complexities there, but I think that's all you really need to know about that. There's one more shape. If we have like a xenon here, there's a fluorine above, fluorine down here, there's a fluorine right there, a fluorine out front, fluorine in the back, and then a fluorine to the side. If you drew a line between all of these fluorines, it would form an octahedron, which is a shape with 8 sides. Or it's like there's a fluorine here, fluorine there, fluorine there, fluorine there, a fluorine up, and a fluorine down. It's like the triangles are forming an 8-sided shape. This is octahedral geometry. So, really briefly, now we'll just go into bond angles and angles between things. If a line is straight like this is 180 degrees. So the bond angle on a linear molecule is 180 degrees. Here, it's like we're taking a whole circle, 360, and dividing it 3 ways, and that's going to be 120 degrees bond angle for this, for a trigonal planar geometry. Then here, this is like a tetrahedron, right? So we have the C right there and an H. They measured the bond angles between these trigonal bonds, and it's 109.5 degrees. That's the only really weird one that you'll see. Now with this trigonal bipyramidal, there are a few different bond angles. If you go from one of the polar bonds, the ones that go upwards and go downwards, to one of the flat ones, like this distance, that's 90 degrees. But if you go between one of the fluorines that's on the flat triangle to another one on the flat triangle, it's the same bond angle as this one, right? Because that's basically forming the same shape there in the middle. So the bond angle between 2 of these is 120 degrees. And then if you go to xenon, the bond angle between any of them is 90 degrees. It's like the corner of a square. So those are all of the bond angles. I'm trying to think if there's anything that's really important to talk about with these shapes. You'll have to take these shapes into account when you're trying to decide if something is polar or non-polar, right? We talked about how the bent molecules will be polar. You could also think about trigonal pyramidal here with the unbalanced lone pair on the nucleus here. That's going to be polar as well, because that dense charge will be more negative on this side of the molecule and more positive on the other side of the molecule. If we think about this, like these are kind of equally distributed. All of these, this is going to be a non-polar molecule. So I'll give you kind of a little bit of a rule for figuring out if your if your molecule is polar, then essentially all of the electronegativities should balance. So let me draw another one of these that we can just use to compare. All of these electronegativities are the same, and because they're equally distributed around the central atom and there's no lone pairs on the central atom, then this is going to be polar. This would be polar because this electron is pushing these other ones down. In a similar way, this is also polar. Even though you might be tempted to, like, let's say we had C and then, let's say we had oxygen in the middle and then there's an H over here and an H over here. You might be tempted to say this is linear and everything's balanced, so this is nonpolar, but really those two lone pairs are pushing the bonds close together. This is water, by the way. That's a polar molecule. So now if we imagine there were no lone pairs on this again, you might be tempted to say that this is nonpolar because everything is balanced. The chlorine, however, has a different electron negativity than the two fluorines. Those are going to pull electrons closer to that side of the molecule, meaning it's more negative over here and more positive over here. This is a polar molecule. So when you're trying to determine if something is polar, you're probably going to want to draw it. So like, let's say we had CH3F. And I say, okay, let me draw this. You just see there, H, there are four bonds, so it's going to do this tetrahedral one. And then an F up here. So there's no lone pairs on this, so that's a good sign. However, there's different electron negativity, so that's going to make this polar. However, if this was an H, then it's nonpolar. Or if all three of these were fluorines, then it would be nonpolar. Okay, hopefully that helps you remember how to understand these shapes and how to figure out if a molecule is polar based off of that information. Okay, moving on, we're going to talk about percent yield. So I think I might have talked about this in the last review video that I put out, but percent yield is just equal to actual yield over theoretical yield. Like this. So theoretical yield might be the number of moles that you calculated, or the number of grams of your product that you calculated using just your equation. And then your actual yield was something smaller because maybe there's some other factors at play, like not all of it would convert into the products for whatever reason. So you can have a problem that says something like your percent yield, or okay, let me write a simpler version of this really quick. Let me just write an equation. We're just going to do, let's say you have sodium chloride plus calcium equals calcium chloride plus sodium. To balance this, we're going to need a 2 right there and a 2 right there. Now let's say you start with 45 grams of sodium chloride, and then you produce maybe 50 grams of calcium chloride. What was your percent yield? So I'm going to look at this and say, okay, this is an original amount of reactant. We can take this over our equation and try and figure out how much in theory we should make. This is our actual yield right there. So if we get our theoretical yield by using this number, then we can calculate our percent yield. And we just do 45 grams of NaCl times the molar mass, so that's going to be 1 mole of NaCl over its molar mass. I cannot remember that off the top of my head. Let me look it up real quick. So NaCl, the molar mass should be about 23 plus 35.4. And then I'll think about ratios. So for every 2 moles of NaCl, then we'll produce 1 mole of CaCl2. So I'll say 2 moles of NaCl there, 1 mole of CaCl2. And then I'll convert that to grams, again, using the molar mass. So 1 mole of CaCl2 is equal to 40 plus 35 times 0.4 times 2, because there are 2 chlorines in there. and that's grams of CaCl2. Now all the units will cancel out except for grams of CaCl2. If I do all these factors, or all these operations, we'll have 45 times this number divided by 2 and divided by this number. Then I will get our theoretical yield. And then we can just take that number and divide it by this number, and that will be our percent yield. In theory, we could work backwards, right? If somebody said our percent yield was 45%, and our actual yield was 50 grams, and our theoretical yield was, actually, I'm not even going to tell you the theoretical yield. You could, in fact, work back and start to see how much product you started with. So you could say 0.45 equals 50 divided by x, our theoretical yield. Then to solve for x, we times both sides by x, cancel that over here, and divide both sides by 0.45, cancels that over here. So x equals 50 grams divided by 0.45. And now that is our theoretical yield of grams of CaCl2. And we could work backwards using the same procedure. So we could convert that to moles using the molar mass, then use mole ratios, say 1 mole of this is equal to 2 moles of that, and then convert the moles of this to grams using the molar mass, and we figured out, in theory, how much reactants we started with. So that's how you would use that in a problem, and you could work it both ways if you wanted to. Okay, moving on. We have a pretty specific problem here. On this paper, it says the volume of chlorine needed to produce a gram amount of sodium chloride at STP. So essentially, it's saying we need a V of Cl2 gas needed to produce a gram of sodium chloride at STP. So in theory, let's say we have sodium plus chlorine, 2, equals sodium chloride. And because the charges of this is a -1 and this is a +1, then you just need 1 each to balance this, because this is Cl2. We need to put a 2 right there and a 2 right there. This is a gas, this is a solid, and this is a solid. It's saying we need to be able to figure out how much volume of chlorine do we need to produce a gram amount of sodium chloride at STP. And STP means we're at standard temperature and pressure. That means our pressure is 1 atm and temperature equals 273.15 Kelvin. That's the same thing as 0 degrees Celsius. Okay, let's say that we wanted to produce 54 grams of sodium chloride, right? So we convert this to moles using the molar mass, the same one that we used just previously, 23 plus 35.4-ish grams of sodium chloride gives us 1 mole. And now we use mole ratios. So 2 moles of sodium chloride will come from 1 mole of Cl2 gas. So 2 moles of NaCl give us 1 mole of Cl2 gas. And then if we take this through, we'll get some number. I'll call this X. This will be X moles of Cl2 gas. And now we want to convert this to volume. So there are a few ways we can do this. One of them is just PV equals nRT, our gas law equation. We know N, we know P and T and R. We just don't know V. So if we solve this for V, it will be our moles, X, times R, which is 0.082058. That's on your equation sheet. Times 273.15 Kelvin. All divided by our pressure, which is 1. And that will give us the volume of Cl2 gas that we would need to produce that amount of grams of sodium chloride. We could also think about it as at STP, right? 1 mole of gas will be 22.4 liters. So I could just think, okay, well, times X moles of Cl2, and for every 1 mole of Cl2, and I put it on the bottom so that our units will cancel, we get 22.4 liters of gas. And so we times X by 22.4, and we know how to solve for that answer. So that's how we would approach that problem. Let's move on. Okay, now we are moving on to solubility calculations for saturated solutions. So the solubility of a certain substance is a measure of how much of a solute you can dissolve in a certain solvent at a certain temperature. So let's say the solubility of salt at 25 degrees Celsius is 53 grams of NaCl, this is table salt, per 100 grams of water. This means for every 100 grams of water, we could dissolve 53 grams of salt in it at 25 degrees Celsius. So, if say I wanted to dissolve 45 grams of salt in 75 grams of water, I could think, how much will be left over from this? So what I take my initial amount, 45 grams of NaCl, and I would say, okay, for every 53 grams of NaCl, or for every 100 grams of water I can dissolve 53 grams of NaCl in this. I just swapped the top and the bottom so that we could cancel out grams of NaCl. And if I do this math, I'll get some number x, and that will be in units of grams of H2O. In theory, that's the maximum amount of water that I would need to dissolve that much. If this amount of water is less than this, then all of this will dissolve, right? We have more water than we need. But if this amount of water is more than this, then some amount of our salt will be undissolved. It'll just sit as a solid in the bottom of the container. So let's say I change this a little bit. Instead, let's start with 75 grams of water, which is this amount. Then I use this conversion factor again, so 53 grams of NaCl goes on the top this time, because we're canceling out grams of water. Then those go away, and then we'll have some number x in terms of grams of NaCl. What this number would be is the maximum amount of salt that we could dissolve in that much water. And if this amount is bigger than this amount, then all of this is dissolved, and we have 45 grams dissolved. If this number is less than this number, then we will have dissolved this amount of NaCl, and 45 minus x grams will be left just as a solid sitting in the bottom of the container. So that is how we would calculate some solubility things for saturated solutions. Now you can have different solubilities at different temperatures. Like something might be more soluble at a higher temperature, right? So like let's say we had like this, we had 53 grams dissolved at 25 degrees Celsius, and then we lower it to another temperature where there's a different solubility. Then we would think about, it would have to change to that new solubility. Some of the part that was dissolved might come out of solution and be just a solid on the bottom, right? And then you would still probably have some dissolved. So you would just adjust the amount of salt that you had in there to the new solubility, whatever your new temperature was. If you want more detail about that or more example problems, feel free to email me, but I am going to move on. Okay, let's talk about dilutions. With dilutions, there's one major equation that's really important. It's C1V1 equals C2V2. C here is your concentration values, and that's going to be in terms of molarity, which is capital M capital M equals moles per liter. You could also have some other concentrations here, which might be mass over volume percent, or volume over volume percent, or mass over mass percent. All of these others will be in grams per milliliter. And so if the problem you're working with is telling you to work with one of these types of concentrations, use grams per milliliter as your units. But if you're working with molarity, moles per liter, use those units. And be careful to use the same units all throughout your problem. Whatever the units on your question are giving you, use units, or change to units that you can use. So essentially what's saying is, like, let's say we have a dilution problem where the molarity of a certain solution of, say, NaCl the molarity of it is, say, 0.45 molarity, which means 0.45 moles of NaCl per liter, right? Now let's say we have 0.45 liters of this at the beginning. Then we go along and we add 0.35 liters of water, right? We added this much amount. So this is C1, this is V1. You might be tempted to say we add 0.35 liters, this is V2. That's not V2. We need to make sure to do 0.35 plus the original volume, like that. And it might ask us what our new concentration is. Well, we would just plug our things into this equation here. So we have 0.45 M times V1, which is 0.4, I used the number 0.45 twice. I'm sorry, that's confusing. Let's change this to 0.25. This is also 0.25. So we'll have 0.25 moles per liter times 0.45 liters, cancels out those liters, equals 0.35 plus 0.45, so that's going to give us 0.8 liters times C2, which is something. It's in units of moles per liter. Then, if we want to solve for C2, we'll just divide both sides by 0.8 liters. Those go away. We put it over here. We'll be left with 0.25 times 0.45 divided by 0.8 will be our new concentration, moles per liter. That's pretty much how you do all dilution problems like this. Just think about what your second volume is, what your first volume is, and your first concentration, and then you can solve for whatever you have left. So let's say they gave you these two and they gave you your second concentration, but they didn't give you your second volume. Then you would solve for V2, so C1 times V1 over C2 equals V2, just like that. They might be a little bit tricky and they might say, how much water did you add to the solution? Then you would want to take your V2 and minus your V1, whatever your initial volume is, and that's how much you added, right? Okay, I think we're good. Let's move on. We'll talk about osmotic pressure now. So this has to do with semi-permeable membranes. This happens a lot, like, say, with blood cells, right? So let's say we have a semi-permeable membrane here. And let's say we're really focused on this side. Let's say this is inside the cell. And this is outside the cell. This is like in all of the fluid that your cell is suspended in. So osmotic pressure has to do with concentrations, right? Water would really like it for it to be the same concentration on this side as it is on this side. And sometimes that might even mean there's more material on this side of the semi-permeable membrane as there is on this one. It just has to be the same ratio, right? The same concentration, the same amount of, like, moles per liter. So let's say we have salt on both sides. So we have Na plus over here, and Cl minus, and Na plus, and Cl minus. Now let's say we have Na plus, Cl minus, Na plus, Cl minus, Na plus, Cl minus over here. Now let's put some water in. The people in the study room next to us are having a very good time. Anyway, so if we look on both sides of the equation of the semi-permeable membrane here, there's about the same concentration of solute, the salt, per water, right? There's 2 per 4 molecules over here, two molecules of sodium chloride, right? And over here there's 3 molecules per 6 water. This means you have the same concentration on both sides. This is isotonic. This means the osmotic pressure, which is really just like the pressure of where the water wants to go in a situation like this, is the same on both sides. So now, let's say we had less water on this side, right? This means we have a much higher concentration inside the cell than there is outside the cell. This means water is going to want to rush into the cell like this, so that it can balance the concentration on both sides. This means that this solution is, if we're focusing on this part, this is hypotonic. And this means the osmotic pressure inside the cell is less than outside the cell. It has a lower relative osmotic pressure. So it has a lower relative osmotic pressure. That's why the water comes in to try and balance the concentrations, right? And this is hypotonic. If you were thinking about this, the water would rush into this, and it would make the cell like swell and get larger and maybe even pop if it was bad enough. So let's now think about the opposite. If we had more water in here relative to solution compared with the opposite side, then in a sense we have a lower concentration inside the cell than out there. And basically the water's like, dang, we gotta help this concentration to get lower. Let's rush out and help them. Like this. This is a hypertonic solution right here. The last one was hypo, this one is hyper. This is hypertonic. This has a higher osmotic pressure inside the cell. Means it's pushing the pressure out, water is going out. Osmotic pressure is higher. And eventually what this means is all the water inside your cell is going to rush out into the surroundings. This will make your cell shrink, might even kill it if it gets too small. So that's what's happening, all right? Water goes out. I think that's pretty much all you need to know about osmotic pressure. If osmotic pressure is larger in the area you're looking at relative to its surroundings, water will leave. If osmotic pressure is lower relative to its surroundings, water will come in to help make the concentrations about the same. Okay. Let's keep going. Now we're on to boiling points and freezing point changes when ions are added. Okay, so I definitely talked about this in my last video, so if you want more detail about that, go to the Exam 3 review video that I emailed to you. I'll just go over the equation. I talked about like the concepts behind it, so if you're curious about like why the freezing points and boiling points changes, I talked about it in some depth there. But for now, let's just look at the equation so we can understand how to use it. This should be on your equations sheet, I believe. Let me find it. Okay, so essentially we have delta T which is like the change in temperature of your boiling or your freezing point, is equal to your constant, I think, what symbol does it use? It uses K, times moles of solute divided by kilograms of water. All right, so, yeah. So let's say we have a problem and we were like, you dissolve 45 or 55 grams of magnesium fluoride in 22 kilograms of water. What is the new boiling point? So we have moles of solute. We're going to convert 55 grams to moles. We have kilograms of water already right there. Our K, we need to decide between two K values that are provided to you. There's K of freezing, which is the freezing point, right? That's negative 1.86, I think, degrees Celsius per mole. Or there's the K of boiling, which is going to be, I think, 0.51 is the number it's on the equation sheet. Yes. Times kilograms. So it's in units of 0.51 degrees Celsius times kilograms over moles. Because we're worried about the boiling point, we'll use this one. If they asked us about the freezing point, we would use this one. But we'll do K there. Now let's convert this one to number of moles of just particles, right? So if we convert 55 grams of magnesium fluoride to moles, then we'd use the molar mass here, which is just going to be some number, I think it's 24.3 plus 2 times 19 about. So we're in moles of magnesium fluoride, but we need to think about when this dissolves, how many particles is that going to make? So if we were dissolving sugar, sugar doesn't separate into particles, right? Like this C6H12O6. So we would be done here because one particle like this doesn't separate into multiple. But magnesium fluoride is ionic. When we dissolve that, that's going to separate. So I need to think about how many particles one particle of that is going to separate into. So I think 1 mole of magnesium fluoride, then we're going to have 1 mole of magnesium ions, and then 2 moles of fluorine ions. So then we're just going to have 3 moles of particles. Just like that. So you just think, how many particles does this molecule separate into? And now we have our number, so 55 divided by this times 3. That will be n right there. So I'll say this is equal to x. Then I'll plug this in. Delta T equals K, 0.51, times x. I'll use this symbol, times x divided by 22. And we found our change in temperature. Now we're not done. That's just how much the boiling point went up, right? So now we need to take that number. So I'll say this equals y. And the normal boiling point of water is 100 degrees Celsius, plus y equals new boiling point. And there's no question mark, we figured it out. And that's how you do that kind of problem. You would just switch some of these numbers. If you're doing like freezing point, you would put this number in for right there. Okay, hopefully that's helpful. Let's talk about heat release when a molecule is burned. So let's come up with an example of like a combustion reaction, right? When you're burning something, we'll have CH4 plus O2, and this is going to make CO2 plus water, right? Now I'm looking at this, it's not quite balanced yet. We need at least a 2 here to get the same number of hydrogens. That's going to leave us with the right number of C, right number of H's. We have 1, 2, 3, 4. So we put a 2 right there. So now this is balanced. I'll put this 2 a little higher. Now when you burn something like this, it's an exothermic reaction, and you release some energy in the equation. So you could say that your delta H for the, actually I don't think we used that term in this class, sorry. We'll just say that it releases like 450 kilojoules, right? So that means per mole of this that you burn, you produce 450 kilojoules. It's almost like a product, right? We can think of heat as a product or a reactant, which is really useful, especially when we talk about like Le Chatelier and understanding how reaction rates change. So, like for example, if you wanted to produce 2,000 kilojoules of heat, how many moles of CH? Let me say grams. You might see that more often. How many grams of CH4 do we need to burn? Then I can just think, okay, we start with 2,000 kilojoules. And I think, okay, I know that for every 450 kilojoules of energy I need 1 mole of CH4. So I'll put 450 kilojoules here to cancel out the kilojoules. And 1 mole of CH4 here. And then we can just use the molar mass to convert from moles of CH4 into grams. So 1 mole of CH4 times 12 plus 4 times 1 grams of CH4. And we've done it. That's kind of how you would think about like heat when you're producing it in a reaction. If it's exothermic, then heat will be a product, something that you release. If it's endothermic, then heat is a reactant. It's something you need. It's something that the equation absorbs from the surrounding in order to make it happen. Okay, I think that's good right there. Now let's talk about solubility predictions with a solubility table. You've seen the solubility table. It was given to you on the last exam. I don't think it's, I can't really like pull it up and show it to you, so I'm just going to go through a few examples. Like I'll just write some things down and we'll try and figure out if they're soluble or insoluble. Let's think. It's going to be calcium. This is going to be, let's go on to say one more. Okay, hopefully you can see all of those. So I'm just going to look in the table, and under soluble compounds, I see compounds containing alkali metal ions like lithium, sodium, potassium. Hey, we have potassium right there. It says that is soluble, and there are no insoluble exceptions. So this is soluble. Let's look at calcium hydroxide. Okay, I'm looking for calcium. I'm not seeing it in the soluble compounds. Let's look at insoluble compounds. I find hydroxides are insoluble. There are some exceptions. Let's make sure calcium isn't one of those. It says compounds containing alkali metal ions. So that's going to be our first group. That's going to be like sodium, potassium. Calcium is an alkaline earth. That's not an alkali metal. So, and it's not barium. So this is not one of the exceptions. This is insoluble. Now let's look at silver chloride, okay? So under soluble compounds, I see halides. So those are like negative ions in the halogen group. So chlorine, bromine. So it says it's soluble, but there might be some exceptions. Let's look at that. Halides of, oh, silver. Silver's in there. So it's silver plus. I actually gave the wrong charge on this. It's silver plus 1, and there's Cl minus there. So that means that this one is an exception to the rule. It says this is insoluble. Then let's look at sodium carbonate. So I see carbonates are listed under insoluble compounds. Let's look at Any exceptions? It says compounds containing alkali metal ions. Sodium's an alkali metal. So that's a soluble exception. This is soluble. Okay, those are just some examples for using that table. If you want any more information about using that table, just feel free to email me for more examples or questions, as always. Let's keep going. Okay, let's talk about ion concentrations as part of an ionic compound. We sort of touched on this a little bit earlier, but let's say that we had 45 grams of CaCl2, right? And we dissolve this in 0.45 liters of water. The question might ask us, what's the concentration, the molarity of Cl minus ions? What is that? So let's approach this. We convert 45 grams to moles. And this is going to be just the molar mass that we added up from the periodic table. I'll just say this is grams of CaCl2 for 1 mole, right? But now the tempting thing might be to just divide this number by that amount of volume, and then we have moles per liter. That's molarity. We're done, right? No, we're not. We need to see how many moles of Cl minus ions do I make per mole of this. So I'll think in 1 mole of calcium chloride, right? I have 1 Cl minus ion. I have two right there. So I have 2 moles of Cl minus ions. And now I can divide this by our volume, times 1 over 0.45 liters. And now we have moles of Cl minus per liter. That's the molarity of Cl minus ions. So that is a way that we could find the concentration of just ions if we were given like a molecule or a compound, right? So let's talk about a few more things. Let's say we wanted to write a net ionic equation of something. Hello again. I had to switch rooms because my room reservation ran out. So we are picking up where we left off. I think we were talking about net ionic equations. So let's talk about an example, especially one that we were seeing with like acids and bases. So let's say we have sodium carbonate plus, let's say, hydrochloric acid. And because this is a carbonate and it's reacting with this acid, we're going to make CO2, and then we're going to make water, and then a salt as well. Whatever this and this is combined, so we'll have sodium, and we'll have chloride. Then we'll just have to think, is this all balanced? My guess is no. We have 2 sodiums here and only 1 over there, so if we put a 2 right there, that will give us 2 sodiums. We're going to need 2 chlorines. That gives us 2 chlorines, 2 hydrogens, 3 oxygens there, and 1 carbon on there. Okay, we're all good to go there. Now, if we split this up into terms of just which ones are ions, right? We have 2 sodium plus ions plus carbonate minus plus 2H plus 2 Cl minus. This is going to yield CO2 still plus water. And then this is the only one that's still ionic. We have 2 sodium plus 2 Cl minus. So now, this is what you could call a complete ionic equation with everything that's involved here written, and all of the original compounds and the final compounds are written. But you may notice that some of these are different on both sides and some of them aren't. Like here we have sodium, we have 2 sodium plus, and here we have 2 sodium plus as well. Not only do we have the same the same component of them, we have the same charge on those as well. So it's still a sodium plus and a sodium plus over here. And chlorine is the same. It's a Cl minus right there and a Cl minus right there. Those are unimportant, and we'll uninclude them with our net ionic equation. However, if we look at carbonate, right, what happens here is we take an oxygen off of this, and it becomes attached to these two hydrogens. And then the carbonate itself changes structure to become CO2, and it's neutral, and then the oxygen will come with these hydrogens and form water. Now that is something that changes pretty drastically on both sides. We should include that in our net ionic. So we'll say CO3 minus plus 2H plus, and then we don't need to include the chlorine or the sodium because they're the same on both sides. This will yield CO2 plus H2O. There, that's a net ionic equation, really good example, and it's how you might see some reactions with acids and bases happening, and that's how you would do it. Okay, now let's move on. Let's talk about reactions and reaction rates. So we have some graphs here. So this is like the plots of reaction section. So let's say here on this height we have reaction rates. So on this axis we're basically measuring how quickly is the reaction happening, right? It's kind of saying how fast is this becoming the product, or how fast is the product becoming the reactants. And then over here on this axis we have time. I'll use two different colors. Hopefully one of these markers works. Yeah, green, that's a pretty good green. All right, so here we're going to have black is the forward reaction, and green is the reverse reaction. So at the very beginning, like right when we add them together, they're gonna start reacting really fast, so they're gonna have a high reaction rate. But as it continues on, the reaction rate is gonna get slower as more and more of the reactants are converted into the products, until eventually you plateau, and it's the reaction rate is not going any slower than it started at the beginning. It's going a little slower than when it started because there's less of the reactants to react, and for a few reasons, it's just going slower. But now if we think about the reverse reaction, right, like it might start here at 0, like because you don't have any products, you can't reform any of the reactants yet. But as you get more and more of the products, then the rate of the reverse reaction will also get more and more steep, until it plateaus and becomes exactly the same as the forward reaction, meaning that how quickly the reactants are turning into products, that's the same rate at which the products are turning into the reactants. That's pretty much like, it's as if you're in an airport on one of those really long treadmills, right? And let's say the treadmill it's not moving when you start. And you start running at a certain pace, okay, and you're moving down the treadmill pretty fast. But then the treadmill starts to turn on and begins to get faster and faster until at some point it just stops at a certain speed. Maybe it matches your speed. Then at that point you would still be running forward and the treadmill would be running backwards and you would be staying in the same place. You wouldn't be moving because the rate of you moving forward is exactly the rate of the treadmill going backwards. That's kind of what's happening here, right? Right here at this, we call this equilibrium. That's when your products and reactants are balanced, forming equally. It means you have achieved just a state where you won't form any more reactants and you won't form any more products because the rate is the same. So that's equilibrium, when these are the same rate. Okay. We can also talk about another graph. Instead of reaction rates, let's say we just talk about concentrations, right? So concentration, I'll put concentration here. And here, I'm going to use green to represent the concentration of the products. So whatever we're forming. It's going to start at 0, right? And then it's going to become much more concentrated as the reaction happens, and then at some point the concentration isn't going to get any higher. We formed our maximum amount of products. Now if you think about black, like let's say black is the concentration of the reactants, at the beginning we'll have a high concentration of them. Let's say we start even higher, right here, right? But then as we form products, the concentration of the reactants will get smaller, until eventually we plateau. and we don't get any smaller than this point. That means that right when these two have become flat, that is equilibrium right there. So those are the two kind of graphs you might see about reaction rates. Let's talk about some things that can change reaction rates. So there's something called the kinetic theory of reactions. Basically, it's kind of talking about why reactions happen and some factors that affect it. So essentially, it's kind of like you have particles, right? Like let's say this is a particle of one reactant, and then let's see if the red works. This is particles of the other reactant. There are a few things that have to happen in order for these to hit and to change chemically. They have to be moving. So like if they're just sitting next to each other, nothing's going to happen. They have to be moving towards each other. They have to collide and actually hit each other. If they miss, then no reaction is going to happen. They're not going to change. They have to have enough energy. So like, say if I like accidentally barely nudge somebody else, that's not really a ton of energy and nothing's really going to change. But if I run at full tilt into them, like something is going to happen, right? And then the collision has to have the right orientation. So let's say that these two were going to hit each other. This is like one molecule and then this is the other molecule. If they hit each other, then it's just going to like bounce off of each other, no change. But let's say instead that this molecule was like this. Now if they collide, this is going to almost make like a wedge force in between them and push them apart. That's what it kind of means when they have to have the right orientation in order to make a reaction happen. So when we talk about factors that can increase or decrease reaction rates, we're kind of talking about things that make the molecules do one of those things in a more effective way. So let's say we have a bunch of molecules here. If we add more molecules instead of just the one of each that we had before, this means now instead of just having one kind of collision, we could have way more collisions, right? This one could hit that one, that one could hit that one, this one could hit that one. Way more possibilities. Because more collisions can happen, this means your reaction rate goes up. So your reaction rate goes up if you add more reactants. As well, if you increase the temperature of whatever you're mixing together, that basically means you're adding kinetic energy to all of the particles, right? So that means they'll bounce around at higher speeds, which means there are more chances of creating a reaction because they're hitting each other harder and they might be having more collisions more quickly. So that will also increase the reaction rate if you increase the temperature. As well, if you add something called a catalyst, it's kind of like an object that isn't used up in the reaction, but helps to make the things in the reaction either hit each other more often or to have the correct orientation when they do it. So for an example of like a catalyst, let's say you're cutting paper, like that's your reaction. You know, when you start, there's no paper cut, and at the end, all the paper's cut, basically, like you're slicing it in half. Now, if you want, you could just rip it really carefully with your fingers. That would be a little bit harder to do accurately. It would take you a little bit longer. But if you had a pair of scissors, right, you'll be able to cut through it much more quickly. The rate of your reaction will go much faster. And at the end, it's not like your scissors changed into something else. Right? Like you didn't use up your scissors. They still work. They're still the same thing. They weren't like a piece of the paper that got cut. It's the same thing with these chemical reactions. So it's like I added a third something like this. And all this does is it helps these two bounce into each other more often, or it helps to make sure that they bounce into each other the way that will split one and cause a reaction to happen. And they're not used up. You still have the same amount of these at the end, and they're not permanently changed. So, in review, if you add a catalyst, or if you raise the temperature, or if you add more of the reactants, then your reaction rate is going to speed up. If you do the opposite, like if you lower the temperature, or you take reactants out, or you take out a catalyst, then your reaction rates are going to slow down. Okay, another thing about catalysts that's kind of helpful to understand is how they interact with activation energy. So if you remember back in the day, we had these graphs of, I think it was energy over here and reaction, like as the reaction goes on. Then you either have this one or you have one that looks more like this, right? This one's exothermic because it's releasing heat. This one's endothermic. So this lump is the activation energy. This is how much energy you need to add to something in order for the reaction to start. Right when it gets all of the activation energy it needs right here, that's when your reaction starts to actually happen and things change. Same here, your activation energy is a little smaller, but it's still there. You have to add that much energy in order for your reaction to start happening. A catalyst will change the reaction a little bit so your activation energy is less. So instead of doing this graph, you might, with a catalyst, this red one, you might only have to go up right there. So you have to add less energy in order to make it happen. Same with over here, you might have to go only up to there before you continue down. So then you only need that much activation energy. This is another reason why it's easier for your reaction to occur when you add a catalyst. It means you have to add less energy in order to make it happen. It's really nice. Okay. Now we're going to talk about equilibrium. That's kind of what we talked about with the reaction plots a little while ago. In a sense, I suppose let's talk about K sub C really quickly. It's kind of like your equilibrium constant, right? Right here. Essentially, this measures about where your equilibrium is going to be. You have the concentration of your products. So I'll just write product 1 and product 2 over your reactants, whatever they are. Reactants, reactant 1, reactant 2. Right? And this is kind of measuring about where your equilibrium rests. Because you have your concentrations up here, and these are in terms of molarity, moles per liter. Then, if this number is bigger than this number, your K sub C will be bigger than 1, right? If you have like 1.5 over here and 1 right there, then K sub C will be 1.5, which is bigger than 1. That means your equilibrium has about more products than it does reactants. It's more heavily on the product side. Now, if you have a bigger number on the bottom and a smaller number on the top, that means your K sub C is going to be less than 1. That means if you're looking at your equilibrium, that's going to lean more towards your reactants than your products. As well, something that's important to understand here is you'll only include molecules that are in a gas phase or that are dissolved aqueously. So let me write an example of something like that. Let's say we have potassium bromide plus Cl2 gas. And I'll put all these in. Okay, yeah, in parentheses. So this is kind of a weird example, and I'm not sure you would ever see this in real life. But this is what we're doing. And then that forms potassium chloride plus bromine gas, or this technically is a liquid. I guess let's say that this is aqueous. This is also aqueous, right? So this isn't balanced, and to balance it, we have 2 Cl's over here and only 1 there. Let's put a 2 right there. That means we need to have 2 potassiums. Now the bromines are balanced as well. So we only include things that are in gas phase or that are aqueous. So in order to find our K sub C of this, we'd have our products, This one's aqueous, so we have the concentration of our KCl. But this one's a liquid, so we don't include that. And then we'll look at our reactants. This is aqueous, so we'll include that. And then this one's a gas, so we will include that one as well. And that's how you calculate this. Now, another thing that's important is whenever you have coefficients in an equation like this, and you're calculating your constant here, if there's a coefficient right there, you need to put that coefficient as an exponent on the concentration in this equation. It's kind of like saying you're taking the concentration of sodium bromide and just you're timesing it by itself again because you have twice as much of it, right? And that's where the squared comes from. So if this was, say, a 3 over here, that wouldn't change anything. But this one's a 2, so that needs to be squared right there as well. The Cl, there's only 1 mole of it compared to everything else, so that one doesn't get an exponent. So that's how you calculate your equilibrium constants, if that helps. So now that we've kind of understood how this works, let's look at the same equation and let's say something else was happening. I kind of wanted to keep this up, so I'm going to rewrite it here really quick. So now we're going to talk about stresses, like things that can change or that will change like the proportions of something in the equation. So let's say that we were going to, we dumped all these things together, we'd reached equilibrium, which means our forward rates were the same as our backwards rates. Then, let's say that we added more potassium bromide. What would happen? That's what a guy named Chatelier was concerned with. So, I tend to like to look at equilibrium like it's a seesaw, right? I don't know how much is in each of these things. Like we've already kind of figured out, like maybe it's balanced when there's more of a box on this side than there is on this side, but we've achieved balance. So I like to look at it like that. Then we add potassium bromide, right? It's like we've just added more weight on this side of the seesaw. So now that's unbalanced and the reaction doesn't really like that. It will push until it reaches equilibrium, which means it will convert some of our reactants over here to be products. So maybe they'll take about half of this new stuff we've added, add it over here, and now we've achieved balance. That means if you add reactants, then it's going to convert some of it and it's going to favor this side. You'll see that often in questions, meaning that the reaction will begin to produce more products if you just add more reactants. The same is the opposite if you take some away, right? Like let's say we took this away from our reactants, or we took some of our reactants away, then it's unbalanced, and in order to achieve balance, we would take half of this stuff and we would move it over here, right? This would favor the reactants. That means if we took some reactants away, then we would convert some of our products back into reactants. That would mean it would favor the reactants. So now we've talked about like if you take reactants away or you add them, we can pretty much imagine the opposite being the case for products, right? Let's say we were back to our normal 2 boxes. If we added more weight over here, what would happen? Well, of course, half of it would have to go over here to balance. This would favor the reactants, just like that. And again, if we took some of our products away, like this, then we would convert more of our reactants into products, kind of to keep it balanced. I know that doesn't look like a great drawing, but that's what would happen. So if we add products, it will favor the reactants. If we take away products, it will favor the products. In a sense, if you have a reaction and you want to produce as much of this as possible, let's say you reach equilibrium, then you're like, why don't I just take some of that out? Then boom, you're going to make even more. It's pretty convenient. Okay, so those are some things that will affect equilibrium. Let's also think about heat for different kinds of reactions. Heat we can think of as either being a reactant or a product, right? It's either endothermic or exothermic. If it's exothermic, it's over here. So let's say this produces, you add these together and then you form these and it produces like 50 kilojoules of heat. Now, let's say we add heat. We make the temperature of this reaction warmer. Say like we start boiling it or something. Well, if this reaction produces heat, if we add heat, that's like adding more of a product, right? That's like we just made this side a little bit bigger. That means this reaction is going to try and balance. It'll take part of that part, move it over to the reactants, and achieve balance. So if we increase the temperature on an exothermic reaction, it will favor the reactants. Now if we take heat away, like let's say we lower the heat, that's like we took away some products, right? Like we took some of this out. That means we're going to convert more of the reactants into products. And so if we lower the temperature on an exothermic reaction, it will favor the products. Now we can think about it the opposite way, right? Like what if it took 50 kilojoules over here plus these other ingredients to produce those? Then if we increase the temperature on our reaction, that's like we added more reactants, makes this side bigger, means we need to take some of that and move it over to the products. So if we increase the temperature on an endothermic reaction, it will favor the products. Now, if we lower the temperature on an endothermic reaction, that's like we took away some of the reactants, right? That means we need to take part of our products and move it over to our reactants to balance again. If we lower the temperature on an endothermic reaction, that will favor the reactants. Now let's talk about what happens with volume changes. So this is not going to be ideal an equation to talk about volume changes. I'll write another one. So let's say we have carbon plus oxygen gas becomes CO2. That's our reaction here. Now I'll draw our little equilibrium seesaw up here. Although honestly it's not as useful for these volume problems, so I'll probably erase it. Now let's say this is all happening in a closed container, right? Now I take this container and I decrease the volume. I squish all of the particles closer together. Now they're bouncing around and when they're compressed together, it's kind of uncomfortable for a lot of particles to be bouncing around. Think of like a gathering that you're holding in your apartment that has more people at it than there should be. Then it would be easier if there were less particles bouncing around and if they could combine to be bigger particles. So essentially what's happening is if you decrease the volume, then the equilibrium is going to push towards the side that has the fewer number of particles. So like if I squish them all closer together, then more of this carbon and oxygen that's in there is going to become CO2. So a decrease in volume favors whichever side has fewer numbers of particles, right? Like on this side we have like 1 mole of carbon and 1 mole of O2, so 2 moles total of particles. And this side only has 1 mole of CO2. So if we decrease the volume, we're going to produce more CO2. Now if we increase the volume, the opposite will happen. Whichever side has fewer number of particles, they're like, hey dude, we got tons of room to bounce around in, let's split up a little bit. Then more of the particles, more of the side which only has fewer numbers of particles will convert into the side with larger numbers of particles with an increase in volume. Okay, now those are pretty much the major factors that will affect your equilibrium or stresses, right? One might think, what about a catalyst? Would a catalyst, because catalysts speed up reaction rates, how would they be a stress here? How could they affect this equilibrium? Well, the thing is about catalysts is they increase reaction rates, but they would increase both the forward reaction rate and the backwards reaction rate. So it wouldn't actually really change where the equilibrium is because it's applying the same increase in speed both ways. In a sense, it's just changing how fast you get to equilibrium, right? We had that graph earlier that kind of looked like this. If you add a catalyst, instead, it will look a little bit more like this. They'll meet each other at a faster pace. It doesn't really change where that line is, it just changes how quickly they'll get there. Okay, so I think we're good there. Let's keep moving on. Talked about the Chatelier. Okay, let's talk about acids and bases, everybody's favorite stuff, right? So we got two major definitions that we'll be looking at in this class. There's the Arrhenius definition, and there's the Bronsted-Lowry definition. I think Bronsted has a weird O like that. Now hang on a second, I'm going to make sure we're still recording. And we are, that's good news. I have been devastated by not checking that previously. Okay, so the Arrhenius definition, the definition of an acid is it's an H plus donor. Essentially, it's something that can give up a free proton, right? That's what H plus is. And now a base is an OH minus donor. So it's something that will yield an OH in solution. So like if you're in water and it dissolves and it gives you an OH ion, then it's a base. I'll give you an example of this one. Here's nitric acid. This is a strong acid and you should definitely know that one. Here's an example of an Arrhenius base, sodium hydroxide. This will dissolve in water and give you hydroxide solutions, hydroxide ions. Now, if we look at the Bronsted-Lowry definition, it turns out it's the same definition for an acid, actually. It's still just an H plus donor. So this is both an Arrhenius acid and a Bronsted-Lowry acid. It's just an acid all the time. Here's another example of an acid. I believe this is sulfuric acid. This is another strong acid. And then an Arrhenius base is the one that's a little bit different. Instead of just being an OH donor, a base by the Bronsted-Lowry definition is an H plus acceptor. Essentially, it's anything that will take hydrogen ions and just attach to them. So let's think of an example of a strong Bronsted-Lowry base. You could even just say hydroxide on itself. That's a strong base. That's going to accept an H plus proton and become water, right? Another example would be like this one's conjugate base. And I'll talk a little bit more about what conjugate bases and acids and bases are in just a second. This one will accept an H plus, right? So that makes it a Bronsted-Lowry base. You could also think of this as it could also give up an H plus, so that could make it an acid as well as a base. Sometimes things can be both of them. They just, you look at what they're doing and you'll determine whether it's an acid or a base based on how they're behaving in the reaction. And I'll talk about that probably right now. So now that we've talked about Bronsted-Lowry bases and Arrhenius bases, let's look at conjugate acids and bases, right? So let's say we have nitric acid here, and it's just going to react with water. Let's react it with OH, so this will neutralize. Okay, so this is going to yield something in solution. This is the acid, nitric acid. It's going to give up its hydrogen. Let's actually not use this. Let's do HSO4, that base that we looked at just previously. So we'll look at this. I guess this is kind of confusing. Let's do just SO4 2 minus, like this. Okay, so this is going to give up a proton, right? And this one is going to accept a proton. So we think about what happens. NO3 becomes NO3 minus, and sulfate becomes monohydrogen sulfate. So it has one H and it has one minus charge now. So this is an acid, right? But then you think about what it becomes. It becomes nitrate over here. Now nitrate, in theory, could accept a hydrogen, a proton, right? This makes it a base. And because they're kind of related, right? Like this became that. This is an acid-base conjugate pair. So if you're wondering what the conjugate base of this acid is, think, okay, what would it become if I just removed one proton? Same for this. This is a base, right? But now we've added a proton to it. It becomes an acid. It could give up that H if it wanted to. So this is the conjugate acid of this base. And then you can just think, okay, how do I get the conjugate acid of something? I just need to add one proton to it. And if I want to find the conjugate base of something, then I just need to take away one proton from it, one H, right? In theory, we could have this going the opposite way, right? We could have HSO4 minus plus NO3 minus becomes nitric acid plus this sulfate base. Right? In theory, like this is the acid here. It becomes sulfate. That's the conjugate base. And then this here is our base. It becomes this. This is the conjugate acid. Okay, hopefully that helps with conjugate acids and bases. Let's now go on to like naming acids and bases. So I'll tell you that the rules for naming acids are a little bit harder or more complex than naming bases. Bases are pretty much just the name of whatever ion it is. Like here we have a base. This is an Arrhenius base because it yields hydroxide solutions, hydroxide ions in solution. You just name this is just sodium hydroxide, right? We just called it the same thing that we would when it was just an ionic compound. That's all you do for bases. Just name it like the same way you would normally. But now let's talk about acids. The trick for acids depends on a couple of things. So first, you have an H, right? That's almost what defines it being an acid. And you think about what it's attached to, whatever this part over here is. So let's say it was something that ended in IDE. Right? So let's say it was chlorine. The name of this, if you were naming it like an ionic compound, this would be hydrogen chloride. Right? H plus Cl minus. But because it's an acid and it has a hydrogen on it, we take the rule for IDEs, which is start with hydro. And then you put the root of whatever this is named. So like chlorine is chlor, right? So I'll write root here. And then you end it with ic, acid. So here, it has an IDE ending, chloride. So we start with hydrochloric acid. This is hydrochloric acid. Let's do a few more. This is hydrobromic acid. Let's do two more. This is hydrochloric this is iodine, so I'm sorry, I spelled that weird. Hydroiodic acid. One more, this one's kind of tricky. We have HCN. This is pretty much the only example of a polyatomic ion ending with IDE, right? This is cyanide. This is hydrocyanuric acid. And there you go. So that's the rule if it ends with IDE. So now let's think about some other acids, like this one, H2SO4. This one is hydrogen and sulfate. Sulfate doesn't end with IDE. I need to think about a different rule, right? So now we think ATE endings. Then you also end with ic, but you don't start with hydro. So this hydro thing only comes with the IDE endings. So then you end it with ic, and you take like the root of anion name. And then ic acid. So here we have sulfate. This is sulfur, because it's taking the sulf from the sulfur, and then you have an ic ending acid. This is sulfuric acid. Let's do this one. This is phosphoric acid. That's phosphate. Right? Let me think of another one. Here's another one you should definitely know. This is nitrate, right? This is nitric acid. Okay? Now there might be some slight changes to this. Now if your anion, this part, let's say instead of, like let's look at this right here. This is, I think that's chlorate, right? You just call this chloric acid. But now, if we had this instead, ClO4, the name of this is perchlorate, right? This anion, you still hold on to the the prefix before. So this becomes perchloric acid. So you still have the same prefix as you would normally, and then there's a chlor, and then you change the ate to an ic. If you want a way to kind of remember some of these prefix changes, think what I ate was icky, I guess. That's the one I learned. So if what I ate, the end of here was icky. So now let's think about ites. So I think here's an example, HNO2. This is nitrite, right? So that's not an ATE, we end it differently. ITE endings, we have root of anion, and then us, acid. So instead of being nitrate, this is nitrite, so we do nitrous acid, right? So this is nitrous acid. Or like this with chlorite, this becomes chlorous acid. And just like the other prefix, perchlor, now if we do HClO like this is hypochlorite, right? This is hypochlorous acid. And that's pretty much how you name all the acids. If you want another way to remember this, I mean, I guess it's free advertising, but the one that I learned was Sprite is delicious. I don't know if there's a better one out there. There probably is. But, what I ate was icky, and Sprite is delicious. And, I don't know, just IDE is hydroic. So those are the naming rules for acids, and pretty much if you see something that can be an acid, you name it like that, and you name bases with the hydroxide ions normally. Okay, let's talk about a few just really quick characteristics of acids and bases. So these tend to taste sour. They turn litmus strips, they turn them red, right? If you got some of this on your arm, it would probably sting, depending on how strong of an acid it is. And honestly, those are probably among the best characteristics of an acid that you can just remember. Over here, these would taste bitter, right? They turn litmus strips blue, and they feel like really slippery. Bitter, they might feel chalky. They're hard to hold on to. You can think of like soap. Soap is a good example of a base. It's slippery. It might be even a little numbing. Might feel really smooth. Those are some characteristics of acids and bases. Okay. So now let's talk about another kind of equilibrium constant. It's kind of like it's a variation on this theme right here. You know, remember the KC of earlier? It's like products, concentration of products over concentration of reactants. Well, now we can have specialized version of this equilibrium constant for acids and bases. K sub A and K sub E. This is for bases and this is for acids. Essentially what this is measuring is just how well an acid will dissociate in water. So if you're thinking about how well it'll dissociate, the acid itself will be a reactant, and then you'll have the H plus ions that will come off of it, right? And then you'll have whatever is left, whatever the acid minus an H would be, is what this A means. And then on the bottom, you would have the hydrogen still attached to the A. This would be the reactant before it splits up, right? And so, if you think about this, if this number is bigger than this number, then you'll get a K sub A of bigger than 1, which means more of the acid will dissociate in solution, which makes it a stronger acid. So the bigger your K sub A is, the stronger your acid is. The lower your K sub A is, that means the more of undissociated acid you have, and the less of it split up is, that means the weaker the acid you have. You can kind of think of the same thing for bases over here, right? So we might have hydroxide concentration here, and then your base without that hydroxide over your base with your hydroxide. So if this doesn't dissociate very well, you'll have a small number up here and a big number there. If this does dissociate very well, I'm sorry, that means you won't have very much of this because it will have split into these two things. It means your K sub B will be bigger than 1. So the larger your K sub B is, the stronger your base. The lower it is, that means more of this you have. That means less of this. This means less of this is dissociated. That means the weaker your base is, right? Okay, now we're going to talk about another thing is in water, because water is pretty adept and become either hydronium, H3O plus, that's kind of like water just attached with another hydrogen ion. That's acidic, right? Because acids yields these. So that is equal to hydronium. So in water, we'll have a certain pH of hydronium, right? And we'll also certainly have a certain concentration of OH minus. Now that's a base that would accept a proton. That means OHs are going to make your solution more basic. If you added an H here, that becomes water, right? Because it will balance out that charge. So in water, water kind of forms both of those pretty evenly. It's been measured that the K sub W K with water is the sub here. That is equal to 1 times 10 to the negative 14. Pretty small number. And because it's pretty much all split into hydronium or hydroxide, then it's just equal to H3O plus times the concentration of hydroxide. Right? It's just the concentration of this times this equals this. And that's really, really consistent in acidic or basic solutions. Is if you know one of these, then this number divided by that number will be this number, right? You just solve for the other concentration. This is a really good tool. Remember this pretty well. It's really, really nice. Now, if you want, you could also think like when your acid is here and it dissociates and gives you an H+, that just connects to this. Pretty much the concentration of your hydrogen ions is pretty much the same as your concentration of hydronium, right? Because this just attaches to a water that was just hanging out in the solution beforehand. There's really no difference between the two of these. So like pretty much this equals this. That's just something to remember. In case you're ever confused and you're like, how do I convert from just H to hydronium? It's just, imagine there's more water that's just hanging out in the solution. It will freely bond with the hydrogen. It creates hydronium. That's why sometimes you'll see this instead of just H, or sometimes you'll see H instead of hydronium. They're really equivalent. Okay, so now let's get into pH. It turns out that when you're dealing with numbers like this, scientists don't super love it. Like maybe you'll find your concentration of hydronium is like 2.5 times 10 to the negative 11th. And they're like, that is a really janky number, and it's kind of hard to understand that. How could we relate these two numbers in a way that is easier, more intuitive, and might be better? And the way they decided to do that was to take the logarithm of this number, and then because this is a small concentration, it has a negative exponent, it will give you a negative number. They're like, let's not have negative numbers, that would be inconvenient. So we take the negative logarithm of it. Then that will give you a number that's a little bit easier to deal with. So let me pull out my calculator. The negative log of 2.5 times 10 to the negative 11th. That is going to be equals 10.602. Now this number only has 2 Sig Figs, and we talked about earlier, we would round to the second Sig Fig, so it's 10.60. That's the negative logarithm of our hydronium concentration. So in a sense, that's kind of the definition of our pH, right? Our pH is the negative log of our hydronium concentration, whatever that is. Or you could also say your hydrogen concentration, just H+, right? They kind of mean the same thing. If you want to, you can also do the same with the hydroxide concentration. So your POH equals the negative log of your OH concentration, right? And because you know that these will multiply together to be 1 times 10 to the negative 14, and then these will give you those exponents, you know that the sum of those has to be 14. That's another way that you can solve these kind of problems, is you know the sum of your pH and your POH equals 14. It's just kind of pretty foundational, and it's because of this number right here. So let's say you had, let's do an example problem. Let's say that your hydroxide concentration was maybe 3.65 times 10 to the third. And your question is asking, what's the pH here? Well, there's really 2 ways that we can approach this, and I'll talk about both of them. One of them is that I know 1 times 10 to the negative 14 equals the hydroxide concentration times this number times 3.65 times 10 to the negative third, because we know that 1 times 10 to the negative 14 equals H3O plus times your hydroxide, right? And then I just solve for that, so I divide both sides by this. I would be careful and use parentheses here in your calculator. That's an easy mistake to make. You might divide by only this part and then times by that. Do parentheses around this whole part. Be really careful with how you plug this into your calculator. Then that will give you the hydroxide solution. And you know, if you just take the negative logarithm of this, then you'll get your pH. So the negative log of 1 times 10 to the negative 14 over 3.65 times 10 to the negative third, that will give you your pH, and you've done it. There's also another way to do this. I could take this number and find the pOH of it, right, the negative log of 3.65 times 10 to the negative third. That will equal my pOH, because that's the definition of the pOH. And I know that 14 equals pH plus pOH, so I could just do 14 minus this number, the negative log of 3.65 times 10 to the negative third equals my pH. I just solved this equation for pH. And that's another way you can solve this kind of problem. Those are some really handy tools for you to be able to calculate pH and pOH. As well, if you wanted to, you can also do P of K sub A and P of K sub B. The idea is that again, these might be in with exponents that you really don't like. So let's say you just take the negative log of K sub B. That will return you pretty much the exponent times a little bit something extra of whatever this was in the beginning. So it's just the negative log of this whole thing right there. And this will be the negative log of this. So let's talk about some things that might be not super intuitive. Let's say your H plus concentration equals 1 times 10 to the negative 1, right? And then your hydroxide concentration is equal to 1 times 10 to the negative 13. You know, you multiply those together, you get 1 times 10 to the negative 14, that's just fine. So that is a really large concentration of hydrogen ions. That means this is going to be really acidic. However, if we take the negative logarithms of both of these to find the pH and the pOH, the pH, right, is 1. Now that feels a little bit not quite intuitive, right? We might think that this is really just, it should be a big number because it's so acidic, right? So sometimes things will move in the opposite directions that we think. The pOH here will be 13. Those will sum to 14, so we're all good. But that kind of means that sometimes when you take a negative logarithm, you get a number maybe that's smaller than you expected, and that's kind of how it works. The negative logarithm will take the number that's smaller, this number, and it'll return a larger exponent. Same thing is happening with K sub A here. If K sub A is really large, and if you take P sub K of A, then you might get a smaller number. So like let's say this was 10 to the negative 1, this will return 1. K sub A is 10 to the negative 2, P sub K of A, P K of A is 2, right? The smaller this number is, the bigger this number is. Hopefully that makes sense and makes logarithms just a little bit more intuitive. Okay, we're almost done, at least for today. We're getting close, I can feel it. Okay, so we're going to talk about 3 kinds of reactions that happen with acids, right? So we'll have a metal plus acid, and then we'll get a carbonate compound, this is carbonate, plus acid, and then we'll have a base plus an acid. This is specifically, this is called neutralization. It's like you're canceling out the effects of both of them, right? So let's come up with an example of metal plus acid. Hopefully you can see that. I'm going to check real quick. Yeah, I think you can. I know it's a little dark up in that corner, I'm sorry. But yeah, so let's say we have sodium plus hydrochloric acid, right? This is going to become the metal plus, it's going to become a salt plus hydrogen gas. So a salt here would be sodium plus chlorine, NaCl. That's table salt, we eat that all the time. And then you're going to make hydrogen gas. Now this is not balanced, of course. We have two H's over here, so we put a 2 right there. That means we need a 2 right there. That means we need a 2 right there. Now it's balanced. So every time you have a metal plus an acid, you create a salt, which is like a metal and a non-metal, plus hydrogen gas. So this would be the same if we had like potassium here. This would just change what kind of salt it was. Or if we had calcium here, then it would create this calcium, it would create this salt and hydrogen gas. So I'll write that as salt plus hydrogen gas. Here we have some compound that has carbonate into it. So if we draw it down here, this will be some ionic compound, right? Like let's say we have sodium carbonate plus an acid. Let's call it hydrobromic acid this time. This is going to create three things. It'll make a salt, again, which will be just NaBr. The charges will be the same, so there's only one of each. Plus CO2 plus water. Essentially what happens is the H goes, two of the H's here goes with one of the oxygens, makes water. The rest of the CO becomes CO2 gas, and then the positive anions will go with the negative anions from the acid, and it will just become a salt. So here's our salt, there's CO2, and there's water. This isn't balanced, of course. We need to put a 2 right there to get equal hydrogens, and then a 2 right there to get equal bromines, and then we have the same number of everything else, so we're balanced, we're good. So this is carbonate. This will always equal a salt plus CO2 plus water. And the salt can change depending on whatever the anions is. Like if this is Cl, then this becomes Cl. If this is nitrate, this would be nitric acid, or nitric acid, then this would become sodium nitrate. If this was not sodium, but it was potassium, then this would become potassium nitrate, and so on and so forth, right? Like these are just salts. And so, now we'll look at base plus an acid. Drop my eraser. Let's think of some examples. So let's think of something that will accept a proton. I don't know if this would particularly happen, but let's say we have this compound right there plus an acid. That's nitric acid. This is hydrogen sulfate, and this would accept one more hydrogen, right, which makes this a base. Then I believe, oh, hang on a second. We're going to pause it actually, and I'm going to try and come up with a great example for this. Okay, here's another example of a base plus an acid. Right, and these, I'm going to use Arrhenius bases and acids. So let's say we have potassium hydroxide. This is our base, right? It yields OH solution ions. And then we'll have hydroiodic acid. This is going to make a salt plus water, right? The hydrogen will come over here with the OH, that'll make water. And then the negative ion here, the iodine, will come with the potassium and make a salt, Ki. So a base plus an acid, this is a neutralization reaction, will produce a salt plus water. Okay, so those are pretty much what happens when you add acids to these different kinds of compounds. You'll be able to predict it's like a salt or hydrogen gas or water and CO2. Pretty much all of these will have a salt. 2 of them will have water and this one will have CO2. Now you can do a little bit of practice to talk about like how much of something you would need to neutralize. Like let's say we had this equation here, right? And let's say that we have 500 milliliters of a solution which had hydroiodic acid, right? And the concentration of that hydroiodic solution was 0.45 molarity, like this. So now, if I wanted to add a certain amount of a basic solution in order to neutralize all of it, and let's say that our basic solution was 55 or 0.55 molarity KOH, right? And I need to figure out how much of this I need to add. So I'm looking for milliliters of this. Milliliters question mark. This looks pretty similar to our C1, or I'll slot Ca for acid. Va of acid equals Cb of base, Vb of base. And we'll just need to be particularly careful that the moles of each balance out, right? So let's start with this amount here. Molarity is in liters, so I'm going to write this in liters. Say we have 0.5 liters of hydroiodic acid. Then we're trying to figure out how many moles of that acid we have. So we'll use the molarity. So times 0.45 moles per liter, moles of HI per liter, right there. And the liters will cancel out. Now we're in moles of HI, and I think, okay, how many moles of KOH do I need to neutralize 1 mole of HI? It looks like it's just 1, so that's convenient. We'll just use 1 mole of HI here on the bottom to cancel out that unit for 1 mole of KOH. And here again, these are coefficients. So if I had like a 2 here, I'd put that right there, 2. Or if this was a 2, I'd put it right there. Now we're in moles of KOH. I can convert to liters using the molarity. So 0.55 moles KOH per 1 liter of solution. Now we're in the units of what we wanted. I guess we could just switch to milliliters, right? Like there's 1 liter, there's 1,000 milliliters. Now we're finally in milliliters. That would be our answer. In a sense, what we did was this CAVA equals CB, VB, but just being careful with mole ratios in the middle. So there are a few more topics that are going to be covered in the final. However, they're going to be taught in lectures either next week or this week, depending on when I get this video out. So I'm going to send like a little addendum to this video that just covers those topics. It should be much shorter. I hope this was useful. I know it's super long, so I'm going to include timestamps to different parts of the video for different topics so that you can just focus on what you want to. Again, I really hope this is helpful. You're going to do great on the final. Send me emails if you have any more questions or you'd like more practice problems for any of this, or you want to go into any of these topics in greater depth. Thanks. I hope you do well.